you guys know. Okay, hey everyone. We're just going to review for midterm 2 for 301. So we're going to start with the K-maps because that was the first thing he said we need to know. And going back to K-maps, let me draw those out. K-map looks something like this, and usually we're given, it's like a square here. And if we have two variables, one of them could be x1, the other x2 or something. It could also be like x, y as your 2. And remember, we start with the 0, we go 1, and we have a 0 here, we go 1. And then what we call the space in here is m0 because it's 0, 0. And then here it is going to be m of 1 since it's 0, 1. And then here it's going to be m of 2 and because it's 1, 0. And then here it's going to be m of 3 since it's 1, 1. Okay, so that's just a little review of the K-map for one variable by one variable. And so that'd be that first example. And then we're going to look at the larger K-map here. And the larger one, if you guys remember that, that's going to have two variables on one side and two variables on the other side. And so it's going to look something like this. We're going to draw our 4 columns and have our 4 rows. And that will be where we have. And then for our variables here, we can say x1, x2, and then here we're going to have x3, x4. And if you guys remember how it's going to go 0, 0 for the first column, and then it's going to go 0, 1. But remember, due to the gray code, it's going to be 1, 1. You can only change 1 at a time. And then here it's 1, 0. So we could only change 1. So we changed the 0 to 1. We changed the front 0 to 1. And then we changed the back 1 to 0. And then here we have our 0, 0. Next one, we have 0, 1. And then we have 1, 1. And then we have 1, 0. And so those are what we have here. And then if you guys remember the insides, it's going to be m of 0. Down here, it's going to be m of 1. Because we start at 0, 0, 0, 0, and then 0, 0, 0, 1. And then here, it's going to be m of 2 because it's 0, 0, 1, 0. And then here, it's going to be m of 3, 0, 0, 1, 1. And in binary, convert that to decimal, and that's how you'll get those numbers. Over here, it's going to be m of 4 because it's 0, 1, 0, 0. And then down here, it's going to be m of 5. Then keep going. You guys will get it. M of 7 here, you got to watch out always because this one's actually m of 6 because 0, 1, 1, 0 is 6, but 0, 1, 1, 1 is m7. Just be careful with that. Remember, go to the last column. Don't use this column because going in order, 0, 1, 2, 3. And you got to be careful on that because people make errors there. This would be m of 8 because it's 1, 0, 0, 0. Convert that to decimal. This would be m of 9. Here we would have our m of 11, actually. And then down here would be our m of 10. And then at this point, right in here, we're going to have our m, and then it'd be 12. And then here we're going to have m of 13. And then here, we're going to have m of 15. And then for final one, we're going to have m of 14 here. And so that's just remembering what he could give us because I'm going to do an example now. And you need to know where those m positions are. So let's do an example. And I'm going to write that over here. So for example, it's going to say minimize the SOP function. And so when we see that, it could be given like x1, x2, x3, x4. So 4 variables, for a K-map. That's what you should think of immediately. And then it's going to have the sum, so the sigma. And then it's going to be small m. When you see small m, that means sum of product. When you see big M, and it would be a pi, not a sigma here, that means product of sum. And so here, when we have the little m, it's going to be 0, 2, 3, 6, 7, 8, 9, 10, 11, and then 13, 14, 15. Okay, so this is what we're given, and we want to minimize the sum of product. I always go backwards on this. So product, I think, okay, in between there's gonna be multiplication. And then at the very end, we're gonna add all the terms. So we're gonna have like terms multiplied, and then we're gonna add all them together in the end. And so that's how I think of it. I go back, so I'm like, do the product, and then sum them all together, those terms. Okay, so now we're gonna draw our K-map here. And for a K-map, we know it's 4 variables, so it's gonna look like this. We're going to have our x1 and x2. So here I'm going to have x1, x2 up here. Then here I'm going to have x3, x4. We're going to draw a line in between and then make sure have your 4 columns and 4 rows. And then once we got those, then you're going to label with the 0, 0, 0, 1, and then your 1, 0, and 1, 1. Okay, so here we go. Our text is going to be 0, 0. 0, 1, 1, 1, and 1, 0. And then here we're going to have 0, 0, 0, 1, 1, 1, and 1, 0. Okay, now we need to fill it in, you guys. And so when we see sum of product, what you're going to do for sum of product, I'm going to tell you guys both ways, but you're going to group all the ones. And then for the next one, you're going to form min terms. And then the third step is you do sum of product for final equation. Okay, on the next one, product of sums, it's exactly the opposite. So group all the zeros. You're going to form the max terms. And then you're going to do product of sum for final equation. So just know they're the opposite of each other. That's how I like to think of it, and it makes me think easily. So you guys know the symbol for both here, like I told before, it's this sigma and it's lowercase m, where here it's pi and it's uppercase m. Okay, now that we went over that, let's fill it in. So I see at spot 0 here, when you have sum of products, you fill it in with ones because you group all the 1 terms together. When you have product of sum, you fill in zeros for these spaces. However, if it says, give me minimize the product of sum, but it gives it to you in this form, this is the sum of product form, so you have to fill it in like sum of products. So, and then you could, then you group the zeros in it. You don't group the ones, but for this one, it's minimize the SOP. So what we're gonna do is we're gonna fill these in with ones, like it says here, because we have 1 terms, which we're gonna group. And so at spot 0, it's gonna be here, spot 2, spot 3. Okay, that's all these terms right here. Then we're gonna do 6, 7, 8. So that'd be 6 here, 7, and 8. And then it's going to be 9, 10, 11. And then we're going to have 13, 14, 15. Okay, so we see all the ones here. What you can do if you want, it's not required, you can put zeros in the empty spots. Some people like to do that, some don't. I don't care. It just takes more time here in an exam, so hurry up. Here we have 8. So that's our largest group. We want to start with the largest groups. So we have 8 of these in here. And then our next group, we're probably going to have to do 4. And what I see right here is here in the corners, there's a group of 4. And then my next group of 4 is right in here. So there's our 3 groupings, and we group all the ones together. Now we need to form the midterms. And to form the midterms, we're going to look at it and see what we get. So let's start with the blue group. So for the blue group, what we're going to get is I'm going to look at these change. So x of 3 is 1 here, and it's 1 here. So when we do this, we keep it the same. We don't put not bar above it. We don't do that. That's for product of sum. So here, the x3 term is 1 for both, so it stays the same. x4 is 1 here, but it's 0 here, so it changes. We don't include it. Here we have the x1, it goes 0 and 1 within that blue grouping, so it changes. And then the x2 goes from 0 to 1 as well. So that changes. So the only one that stays the same is x3. Our next term that we're going to have is let's do the orange group. And so when we do the orange group here, what I'm going to get is, let's look, x of 3 changes from 0 to 1, but x of 4 stays the same. So x of 4 here, and that's 1, so it doesn't have a bar above it. And then x of 1 stays the same. So I'm just going to put that in front for order. And x of 2 changes. Remember, this is sum of products, so these two are going to be multiplied. And then the last one is our pink group over here. So for the pink group in the corners, what we have is x of 1 changes, x of 2 stays the same, but we need a not bar above it because we notice it's 0 here and 0 here, so put the not bar above. And then x of 3 changes, x of 4 stays the same at 0. So let's multiply that by x of 4. Okay, now let's group these terms together in order to form our sum of product for our final equation. So we got our min terms. Now we're going to do the sum of product. So summing these together, remember that's addition between the plus sign for the or. So what we're going to do here for sum of product is the SOP is going to equal x of 3 plus x of 1 times x of 4 plus, and then our x of 2, and then a naught times x4 naught. And so that is our sum of product right here, you guys. And that was how we got it. And that was pretty simple, I would say, for a good review. And now let's just look real quick at the product of sum, and then that should be good. Okay, so let me erase this. Okay, so for product of sum minimization, let's see. Okay, for the product of sum minimization, my example I'm going to use, we're going to have f of x1, x2, x3, and that's going to equal, then I'm going to just do pi here for the symbol, what it should be, and then big M 4, 5, 6. And so that's what it will look like. So when you see a pi symbol and you see big M, it's given to you in the form of product of sum. So if it said here SOP, you would still fill in zeros for these values because this was given to you in the product of sum form. And then you can fill in the rest with ones, and then you group the ones together. But right here, it's asking for product of sum, so we're just gonna circle the zeros that we fill in here. Notice there's 3 variables here. So what we're gonna do for a K-map is draw it out. So let's have our 1, 2, and 3, and 4. And then here I'm gonna have my 3rd variable. And so what's going to happen here is we're going to have x1, x2, and then down here I'm going to have x3, and here I'm going to have 0, 1, 0, 0, 0, 1, 1, 1, and 0. Okay, let's fill in, and we were given in product of sum, so that means we fill in zeros. Okay, so at spot 4, if we remember, I'm just going to make a tiny little, remember at this part, it is 0 here, it is 1, we have 2, we have 3, we have 4, 5, 6, and 7. Okay, so when we fill these in, we're going to have a 0 at 4, we're going to have a 0 at 5, and a 0 at 6. And so if we're grouping these together, what I'm going to do is I don't see any group of 4 we can possibly make. So to group the zeros for product of sum, I'm going to do it that way. And my other combination will be right here. And let's combine those and write the max terms because it's product of sum. So for our max terms for the green group, what I'm going to get is, let's look, x3 stays the same, x1 stays the same. Oh, but remember here, it's a little different because when x3, see how it's 0 and it stayed the same? Because it's product to sum, we do a bar over it. So you do like the opposite of the value it would be here. Because it stayed 0, you make it 1 here. And then x1, since it was 1, we're going to make it 0. x2 changed, however, 1 and 0 here. So that's why I have for the green group. For my pink group, I'm going to have x of 1 stayed the same at 1. So remember, just flip that. And then x of 2 stayed the same at 0. So make that 1 because it's product to sum. And then x of 3 changed from 0 to 1, so we don't include that. Remember, it's product to sum, so we do summing right now. And then when we group them, all the max terms together, that's going to be when we do the product. So for my final product here, what I'm going to get for my product to sum, my function, it's going to equal. And since it is the summing, that in preference order and comes before or, the preference is not and or. So we have to put parentheses around in order to do the or function first here. And then here it's going to be x1 plus x2. And so that is what we have for two groupings for product to sum. And now that we have discussed that, we've done pretty well. The only one I want to bring up, the only other one I can see them really, is reducing costs. And so let's do a reducing cost example. To reduce costs, look at the two functions together. And then choose groups that are common terms in both functions because they can share gates. And that's the biggest implementation that we want. So for step 1, look at the two functions together after you draw the k-maps for both. Choose groups that are common in both functions. And then finally, you do that because they can share gates. And so we're going to be given, I'm going to draw just a k-map for both. This was an example. And so we're going to have two k-maps. One here and one here. Okay, and we're going to have our function and another function here, and we're going to have 4 columns each. Okay, and then we're going to do 4 rows for each one. 1, 2, 3, 4. 1, 2, 3, 4. Okay. Now, when I'm looking at this, I'm like, okay, this one's going to be our f of 1, let's say, and this one's going to be our f of 2. And I'm just going to fill it in with what the values. So it had a 1 here, it had a 1 here, it had a 1 here, we had a 1 here, 1, 1, and then we had a 1 down here. Okay. In this one, we had a 1, another 1, and we had a 1, 1, 1. Then down here, we had a 1. Okay, so now that we've done that, we have our variables up here, x1, x2, x3, x4. This one, same thing, x1, x2. Then we're going to have our x3, x4. And then they follow the exact same pattern as we've been doing before, where this will have 0, 0 here. So 1. Okay, and then we'll do it here as well. Sorry, this takes just a little time to set it up. 1, 1, and 2. Okay, now that we got these together, let's look at them. What do they have in common? Well, when I'm looking at this, I'm seeing, looks like this, oh, can I do a different color? This one right here, if I'm looking, I'm like, okay, this is in common with this one. And then looking here, I see that's what I would say, and I would also say right here. And you're probably wondering, why in the world did I not circle this group over here? Because these two are in common as well. And I agree totally. And I'm like, why should we not? Well, there's a very special case. So the strategy for this, why I'm not collecting that green term, you're going to share the smaller groups. And since this is a 4 variable, our small groups will be 1 or 2 cell, and then independent, which are non-common between the two, groups are okay. And this is 4 cell or 8 cell. So what I'm seeing right now, the reason I didn't group these two green ones together is watch. In each, I can make it simpler by grouping. So watch. See this one? It's an independent group, and that simplifies it because if I shared this term, I'd have to make another term for this one. Here, this one is a group of 4, so that simplifies. And if I did this, if you guys see in purple, if I shared these, I would still have to make another equation for the outliers over here for each independent one. And so then that would actually be 3 equations instead of 2. So for those bigger groups of 4 cells or 8 cells, independent groups are fine. The ones that you share are the smaller groups, 2 or 1 cell. Okay, now that we talked about that, let's write the simplified equation for each. So here for the F1, when I'm looking at this, we're just going to do sum of products for this one. The blue group, this big one here, the dark blue, when I'm looking, X1 stays the same. So, and that's at 0. And then my other one, X4 stays the same. And that was that one. And then for my red group here, let's do that one. That would be X1 stays the same. X2 stays the same. Oh, oops, I just noticed I should be doing products and then you, because it's sum of products. Then the X3 and X4 here, if you see, they change, so that's why we only have X1 and X2. Those are the only ones that stay the same. And then this small light blue here, that the X1 and X2 stay the same, and the X3 and the X4 stay the same. So we're just going to write those as is. So the X1's at 1, the X2 is at 1, the X3 is at 1, and the X4 is at 0. Okay, we got first function. Now we're going to do the other one. So simplify F2. Looking at this big green group here, X1 changes from 0 to 1. X2 stays the same. X3 changes from 0 to 1. X4 stays the same. Let's do the red group. X1 and X2 stay the same at 1. X3 and X4, looking at this, X3 changes, X4 though stays the same. And then our last little blue group here, it's going to be, when I'm looking at this, it looks like X1, X2 stays the same, X3, X4 stays the same. So it's going to be X1 and then not in front of that, and then multiplied by X2, and X2 is 1, and then multiplied by X3, which is 1, and then multiplied by X4, which is 0. And when I'm looking at these two together, oh, I just noticed right here, sorry, I forgot a little knot in front of this X1 term. Okay, when I'm looking at these two equations, you guys are going to see does this one here, this x1 times x2, oh, I forgot my x4 term in here. Pretend there's an x4 term right here, multiplied by x4. That looks exactly the same as over here, what we got x1, x2, x4. And then our other one here, which I'm going to do in different color, is exactly the same as this one here, because those were the shared groups, the red and the light blue. And so those terms are exactly the same here. And now we're going to put the common terms. So since they can be shared, let's count the amount of gates that are used in here. So in this term, what we're seeing is we have, I'm going to point out all the gates. We have one large OR gate here that is putting the 3 minterms, so this term here, and this term too, that's ORing them all together. We're going to have an AND gate, and so for this one here, there's an AND gate. This one here, there's going to be a 3 input AND gate, and then here we're going to have a 4 input AND gate. So when I count those all together, what I'm getting for this, for the AND gates, I'm going to get 1, 2, and 3 for those 3 turns. So 3 of these gates. And for the OR, I'm going to get 1. That will combine all the turns together. And then over here, what we notice is we're going to have these 2 terms will be shared right here. So we can ignore the AND gates going for these 2. So right here, we can ignore that, and we can ignore this because the other one, we already counted how many gates were in. We took those into account, the shared ones. So on this side, we're going to just have one large OR gate ORing all these together. And then we're going to have one AND gate for this term. And so on this side, for the AND gates, we're going to have one gate for that first turn there. And then for the OR, we're going to have 1 gate. And so when we combine these, we're going to get 3, 4, 5, 6. So in total, 6 gates since we have shared cells. But if we didn't have shared cells, it would be 8 gates because we'd also have to take these 2 terms into account. So that's the nice thing. And then you can draw the circuit from it. Okay, now that we talked about that, we're going to get into coding a little bit. And so for coding, what we're going to do for VHDL is it works a little differently. We're going to see the normal coding languages. So let's review the ones that we should know. So let me clear this because he will test us on VHDL code. Okay, let's start with the basic. And so for this, I'm going to stop this one real quick, and I'm going to share a new screen here. So let me pull up my text editor. Now that I got that, I want to see if there's a... Reshare. Okay, here we go. So I'm going to have this here. So let me just make it a little larger. Okay, so we're going to start with our library as always. So make sure your library is IEEE and then end it with a semicolon for the end of the statement. The next one is use IEEE.standard logic 1164.all. And then your next 2 are use IEEE.standard logic arithmetic dot all, and then end that with a semicolon as well. And then use IEEE.standard logic, and then this one I'm going to do unsigned dot all. And so comments are like this when you do 2 dashes. VHDL is not case sensitive. And so you guys know that is a big thing. VHDL is not case sensitive, so it doesn't matter if I have the capital L or lowercase L. Doesn't matter if I use all capitals or all lowercase, doesn't care. And so this is all my libraries right here. So I'm just going to put all the libraries in different colors so we can see it. Okay, so this library up here, IEEE, you need to use that. That's like creating basically your code of bookshelves. So like you have all your bookshelves, let's say the one bookshelf and all the books in it. These use statements are sort of like the individual books in that bookshelf. So here we need standard logic, you know, for inputs and outputs. Here we're going to use some arithmetic. So that's like plus, minus, multiplication, division, and unsigned. That's like for positive and negative numbers. Just always include these 4 statements whenever you write code. Just do it always. It doesn't matter. That's what you need. Because that will cover all the scenarios so far in this class. Okay, now that we talked about that, I'm going to do the entity statement. And so the entity statement is a little different, so you guys know, but once you get it down, you're fine. So entity, and then circuit 1 is. And then this is where you declare your ports. And so I'm going to make A an input, and that's standard logic. So that means 1 and zeros is what A can stand for. Then I'm going to have B, which is an input in standard logic. And so that can be 1s or zeros too, set for B. C is going to be an input, and that's going to be standard logic. That's 1s and zeros as well. And then we're going to have D, which, or sorry, F, I'll just call it to make it simpler, is our output, and that's standard logic. And then you end it with the semicolon here. And so this is what it'll look like. The last statement you don't have a semicolon at because it's right outside the parentheses. Okay, now that we, you have to end your entities with an end statement. So end and then the name of the entity, circuit 1. Okay, I'm going to draw this out so you guys know what circuit 1 looks like. So circuit 1, how I was able to do it is make a box for the entity. If you have to draw it out ever, so our entity here is going to be circuit 1. And within circuit 1, what we're going to have is we're going to have the inputs A right here, like we said. We're going to have B, and we're going to have C. And we're going to have one output F. And so here I'm going to have A, B. Oh, don't worry, I'll make this larger for our next example. So we have A, B, C, and F. Sorry, and it's green. So let me draw it out. What's going to happen in here is now the behavior. So what we're going to write for the architecture behavior, that's everything that's happening inside here. And so that's going to happen in here where the entity is on the outside. So that's like what's coming in and what's coming out of this entity, which we call circuit 1. Okay, so next in our coding here, we're going to have the architecture, behavioral of, and then it's the entity name. And so your entity name in this is circuit 1 is, and then you're going to have begin for your statement for the architecture, and then you're going to finally end the behavioral at one point. And so within here, what you're going to have in your behavior is all the internal, what's happening inside that entity. And so what you need to do, I'm going to, you need to declare your internal signals first. So how you declare an internal signal is you start with the keyword internal. F1 is going to be assigned to A1, A and B. Oops. And this assign, you do it with an arrow pointing towards what you're assigning it to. And then here it's going to be A and B. For signal F2, it's going to be assigned. And what we're going to assign to F2 is going to be C and not B. And then here for F, it's going to be assigned F1 and F2. Okay, so let's draw this out and see what this means. actually here I'll do instead of an and an or just to change it up a little. And then this is the end of the behavior. So see how with the circuit one, for my entity, I had to give the name and say is, declare all the ports, had declare them as inputs or outputs, and say if they're standard logic, so they're zeros or ones, or it could also be a standard logic vector, so a vector zeros and ones. But right here, we just have single bits, not multiple. Then we have to end it. And so that's for circuit one here. And then down here, we have our behavior. So what's happening inside the circuit? So we have this word begin for the behavior, and then you're going to end the behavior. And so always write those when you make this statement. You have to first declare the internal signals, and then what you do is you assign the output what it actually is. Let's draw it out. And for this inside, I'm going to do it in a different color here. And so what we're going to see is I'm going to read off what I have here. A and B are going to assign to the internal signal F1. So let's AND together, A and B. So my AND gate here. And I'm going to call this F1 as my output. And then F2 is going to be C and not B. So I'm going to have a not here. And then C and not B. That's F2. And then F is going to assign F1 or F2. Okay, so I'm going to have an OR gate here for F1 and F2. And that's going to get assigned to F as the output. And so right here's our F on the outside, make it larger. Okay, so that's how the behavior runs. It's all the inside. So the outside's the entity and the inside's the behavior. Okay, now that we reviewed that, that's pretty good to know. Let's talk a little about just the order of operations in VHDL. So now you know how to code a basic circuit for VHDL. That's pretty nice. So the order of operations in VHDL here, let me clear it. This is not code at all, so just this is a note to self. Order of operations, what happens is it's going to start at the not, and then it's going to be the and or the multiplication and division here, and then it's going to be the addition, subtraction, and then concatenation here. That's what that and symbol stands for. And then there's some weird stuff we never talked about, so I'm not going to do that. Then it's the logical comparisons, which are the equal to, the not equal to, the less than, the greater than, and then less than or equal to, greater than or equal to. And then finally, down here, what we're going to have at the very bottom, it's and, or, NAND, NOR, exclusive OR, and exclusive NOR. Therefore, when you have VHDL in your coding, you need to use parentheses for your order of operations. And so I'm going to do an example here. If we have F is equal to X1 and X2, or X3 and X4, your order of operations here is first going to do the go from left to right. So it's going to do it here. Then it's going to do here, the or, and then finally it's going to do here, the last and. So it just goes left to right. It doesn't care. So if you want to actually do these first, you have to put parentheses around them. So if you want the second and this one to correspond to these two and not go left to right, you'll have to use parentheses. Okay, now that we talked about that, what I want to do is I want to just get into a lot of the coding for VHDL, because I feel like that's a large place where we can get better at. So I made sort of a little thing to know the big ideas of what we need to code about. Let's talk about those, and then we can get into the new stuff. Okay, so now that we talked about that, let's talk about multiplexer. So let's clear this all up. A multiplexer, it has an S to select value of W to appear at output. And so what it looks like, if you guys recall, if we have a multiplexer here, and we're going to have inputs going to it, and we're going to get, it's going to select one of those as the output. And we're going to have a select here. And for select, I'm just going to have S of 1 and S of 2. So here I'm going to have S of 1, and then here I'm going to have S of 0. And then for my inputs, it's going to be W0, W1, W2, W3. And okay, so those are our inputs, and our output here is going to be F. And so it selects one of these through the select code. So if it selects 0, 0, we know that's going to be up here, W0. If select set to 0, 1, it's going to select W1. If it's set to 1, 0, it's going to select W2. And if it's set to 1, 1, it's going to be W3. So that's how our multiplexer works. So if we have to code this, big thing to remember is if you have like a sort of truth table, that's when you use behavioral. However, if you have component and port map, that's when you use structural coding. And so I'm going to go into the coding here. And so for code, it's going to be behavioral, since we're going to have a truth table, and that's where it determines our output, if you think of it, because we'd have our S1 and our S0 here. And then we would have which value of W it would select to be our output here. So if we have 0, 0, our value for the output, we can make a truth table from this. It would be W0. If we had 0, 1, our output would be W1. And if we had 1, 0, it's going to be W2. And if we had 1, 1, it's going to be W3. And so just remember that for behavioral coding, you have a truth table. For structural coding, it's component or port map. That's when you know to use structural. Okay, so let me start my code here. I'm going to do it in a different color. I'm going to make it red, and decrease size. So library, IEEE, always start with that. Remember the 4 libraries I told you. Use IEEE dot standard logic, and then 1164 dot all. Use IEEE dot standard arithmetic dot all, and then use IEEE dot standard, and then the last one, if you guys recall, was unsigned, standard logic unsigned. And I just noticed I forgot my logic here for arithmetic. And standard logic unsigned and dot all. Okay, then now we're going to start our entity. So for our entity, what we're going to have, say your circuit name, let's just call this circuit 1, keep it simple. What are ports? So what are the inputs? What are the outputs? So we know the input, it's going to be the select. It's definitely going to select. So we're going to have S, which is going to be an input. And for that input here, it's going to have be a standard logic and then vector, and it's going to be 1 down to 0. And the reason I did 1 down to 0 is because look at my truth table, it starts at 1 and I go to 0. And then for my next port, would you guys say W0, W1, W2, and W3? Those are going to be also, are those inputs or outputs? Because in my truth table here, it's under the output F. And so you guys are probably like, ooh, which one is it? And I'm going to say their inputs because it comes into the multiplexer. If you look in the little diagram I drew up there. So W0, W1, W2, W3. And for this, I'm just going to have it an input and have it as standard logic because it can either be 1 or 0. And then my output, the last thing, F is going to be my output, and that is a standard logic. And if we see, would you guys say that's a standard logic vector? Because like S1 and S0, like looking at that, no, it's only standard logic because it's only going to take the value of W0, W1, W2, or W3. And so that's just 1 bit. It's not going to take the value that select. And so standard logic, and then remember for your last one, you just have the parentheses in the statement ends with the semicolon after the parentheses, and you're going to end your entity, and then we're going to have to do the architecture behavior. So the architecture behavior of, and what the behavioral of your circuit name for your entity. So circuit 1 is, oh, sorry, I forgot the is here for the entity. And the behavioral, if we have to code this, we're going to code it by the truth table. That's the easiest way. And so remember, you always have to begin the behavioral. Oh, that's weird. Change color. So let me decrease that again. We'll do this, I guess, in all different colors just to separate it. Okay, so it's going to begin. And for a behavioral, it's going to be started out. What we're going to have is we're going to assign it. This is when we're going to use with select. If you guys recall, it's a good remembrance if you don't. With S. So S is going to be what's selecting what goes here to the output. So with S select, and then for our output, it's going to be F. What we're going to assign to it is going to be W0 when it's 0, 0 at the input. And then it's going to be W1 when 0, 1. It's going to be W2 when 1, 0. And it's going to be W3 when 1, 1. And so that's our with select here. Remember, use with select outside when you're not in a process statement. In a process statement, you would use the if else statement, but since we don't have a process, it's with select. And you can also use when else. Either one works, whichever one you want. Also, right here, instead of saying when 1, 1, I could have said when others. And that would cover all other cases. And the only other case for this 2-bit would be 1, 1. You can do either way. And so then I would end the behavioral. And then after that, since I ended the behavior, going back, remember you had your libraries, you had your entity, and then you had your behavioral statement. Is behavioral because we could write a truth table from this. And that describes how multiplexer work. Remember, it's based off those select values. That's why we used a with select for our actual code in our behavior statement. Okay, now let's talk a little about how to do a decoder and encoder here. And then after that, I'm going to do the counters. The only reason I'm doing decoders and encoders is because those have the different ones where I feel like it might be a possibility. I don't know with BHDL coding, but he was pretty big on that. So let me just cover that real quick. Okay, let's go into binary decoders. What a binary decoder does is basically, the weird thing about the decoder is it has an enable pin to it compared to the encoder, which doesn't have an enable, but looks something like this, if you guys recall. And then it has 3 inputs. We could have W1, 0, W1, enable, and then 4 outputs, W0, W1, sorry, Y0, Y1, Y2, Y3. Okay, let's, so here for one of my inputs, I have W0. I'll just draw it inside it, W0. Next one, I have W1. Down here, I have enable. Then on this side, I have Y of 0. Then I have Y of 1, 2, then Y of 3. And so we have 2 inputs and we have 4 outputs. That makes sense. It's a decoder. So decoding, it goes from binary to decimal. And so you can represent 0 to 3, which are decimal, in binary with only 2 digits. You can, because remember 0, 0, 0, 1, 1, 0, 1, 1, that represents 0 to 3, but in decimal, you have to have 4 digits to represent those. And so what our truth table is going to look like, if you guys recall, it's going to have our enable, W1 and W0 here. And then over here on this side, we're going to have Y of 0, Y1, Y of 2. Okay, so for this here, enable has to be activated in order for this to work. If it's not enabled, then the decoder is just not going to work. So we have to run through all of our different scenarios here. So it could be 1, 0, 0, could be 1, 0, 1, could be 1, 1, 0, could be 1, 1, 1. Okay, and then whenever it's 0, we don't care about anything else because it's just going to be don't care for output. So here, when we have 0, 0 for a binary, that's going to be 0 in decimal. So here for the 0, it'd be this one here, and the rest would be 0. When we have 1 in binary, that's going to be 1 in decimal. So the rest are 0 here. When we have 2 in binary, it's going to be 2 in decimal. So 0, 0, and then this one for 2, and then 0. And then when we have 3, that's going to be where 1 goes, and the rest are 0. And then down here for the don't care, because enable's off, we do not care. The output is going to have to be 0 because the enable pin's not on. So the outputs, there's going to be no output at all. And so here's our decoder, what it looks like. It basically takes binary number and produces a decimal number. And so since we have a truth table, we use behavioral coding. And for behavioral coding, how it's going to work is, let me get this up here. So I'm now going to do the code. So let me skip a few statements and decrease it to about 18. So I'm going to have my library IEEE here, just to try and fit it all on one page. It might be smaller. IEEE dot standard logic, and then 1164. And then you have use IEEE dot standard logic, and then arithmetic, and then use IEEE dot logic, and then last one is going to be arithmetic, logic. Our last library will be, dang, I always forget this one, unsigned dot all. Oh, sorry, I forgot the dot all at the end. So I would definitely just have these written on something so you just can easily call them. Entity, and then I'm going to call this decoder is, and then for the entity, remember you have to do the port statements. So what's coming in as the input is going to be enable. It's going to be W1, going to be W0. And then, so inputs, those are all standard logic, not vectors. And then our output is going to be Y. And that is a vector, so standard logic vector, and it's going to go 0 to 3, the way I just wrote it in the truth table. And then you're going to have your parentheses to end this, and then have your last, the semicolon for this statement is after the parentheses. And you're going to end the entity, so end decoder. And then you're going to have architecture, behavioral of decoder is, and then for the behavior of the decoder, what it's going to be is we are just going to assign it with the with select. You can also, let me see, for the when else, if we want to get some practice with that, just as a refresher on your VHDL code, let me pull it up so I know how to make sure to do that correctly for you guys. Okay, here we go. So for the when else, what you would do for this one, you have your, oh, remember you have to begin behavior as always. When you begin it, right here, what we're going to have is, let's just code the output and we'll see if we need to add anything else. So when we begin, for the first thing for when else, you declare the statement actually. So you have your output and you set it equal to, and for the output, what it's going to be equal to is it's going to be F is going to get assigned the value of, and if I'm looking at this table, I would say 1, 0, 0, 0, because, oh, sorry, my output's actually Y here. It's going to be 1, 0, 0 when, and then the input is going to be, we forgot to declare an internal signal for the input, and that's why I'm catching it here. In your internal signal, it has to group these three together under one. So I'm going to group it under the name ENW. And it's going to be a concatenation of these three. And so what I'm going to do here in my code, so you guys understand what a concatenation is my signal ENW. For concatenation, how I'm going to do that is basically, it's going to look like standard logic vector, and it's going to have our 2 down to 0 because 3 spaces enable W1, W0. And this signal, what's interesting about your internal signals is they go right before you have your begin statement here. And for the concatenation, it's going to be the ENW is going to be equal to EN and here W1 and W0 concatenated together. And now that we concatenated all those, they're grouped together. So that's under just our input here. What we can think of it is just ENW, and these are our values. So now we have to actually code those certain simulations. So why the output's going to be 1, 0, 0, 0 here when ENW is 1, 0, 0. So when, oops. When ENW is going to be set equal to 1, 0, 0. Y is going to be set equal to 0, 1, 0, 0 when ENW is going to be equal to 1, 0, 1. And then keep going down this truth table. Y is going to be equal to 1, 1, 0 when ENW is going to be equal to, and then that would be 1, 1, 0. So you guys get it pretty much. You just set the output and then you say when. Interesting part here is when you do have the when else, I forgot, so it's a good thing we're bringing this up because you might have to, I like the with select a lot more, you can see, is because I forgot there's a special part of this is, here's the else part. You don't end the statement. And then it's like the with select where you only have to declare the output once. And then, oh, oops. Okay, and then, so for the when else, when, and then else, and then the next one, when, else, and then the next one. And so that's how it's different from the with select. If you remember, we had with s select, and then we had the output set equal to this. and then when, and then we didn't have this right here. We just had the 1, 0, 0. And then you would have then this next one would have the comma, and then comma, then comma, and then at the very end, it would say when others. Here for the when else, you have the when, else, when, else, when, else. And then for going through all these terms, we see we have one more 0, 0, 0, 1, when E and W is set equal to, and then else, and then our final statement is going to be, or when else, if we're doing this correctly, making sure what you need to say is 0, 0, 0, and then that's it. You don't use when others like in a with select. You just have the last one here, and then you finally have to end the behavioral. And then here, when we look back at the code, let's make sure this is correct. We have all of our libraries here. So we have the 4 statements we need. Then we declare the entity, decoder is, and then we have the ports, EN, W1, W0. We have the output of Y, 0 to 3. And then we end the decoder. And then we have the architecture behavior decoder is. And for our behavior, we concatenated these 3 inputs together. And so when we started, so we declared the internal signal from 2 to 0 because we had 3 inputs, and then we concatenated them all. And then here we assigned the output Y, and we assigned it 1, 0, 0, 0, like the truth table said, when 1, 0, 0, 0, 1, 0, 0, when 1, 0, 1, 0, 0, 1, 0, when 1, 1, 0, and 0, 0, 0, 1, when 1, 1, 1. And then the last one, 0, 0, 0, 0. For the statement, the with select, you would just have with ENW select, and then you have the Y, and it's set equal to this when. You wouldn't have this statement right here. You just have the 1, 0, 0, and then instead of the else, you'd have a comma, and then it'd be comma, comma, and then it'd be finally the output when others, and then you'd have the semicolon. So then we ended the behavioral, and that should be our decoder. Now that we talked about that, we went through pretty much a lot of the VHDL through our multiplexer. We did a decoder, encoder, and the other ones are the latches and the flip-flops. So that's where we have a process statement. I will want to introduce the process statement. So I'm going to do the D flip-flop since that's the most common, and that's the one. And then we'll get into counters because he's going to want to know counters for us. Okay, so let's get into the D flip-flop since that one is the most. The T flip-flop he doesn't talk about as much. Okay, so for a D flip-flop, what we have is it's going to be edge triggered circuit only changes once during one clock cycle. And so for this one, what we're going to have up here, let me move this one. For a D flip-flop, it looks like this. I always like seeing the diagram more than the actual. So here, we're going to have an input here, which is our D. We're going to have our clock coming in, so our clock. And then we're going to have an output Q and then Q naught. And so we have our Q, Q naught. And for, if you guys remember D flip-flop, it basically follows the value of D when the clock is positive edge triggered. And so let me code this for you guys to just show you. So since it follows the value of D, we can make a simple truth table for this because it's just literally if clock is 1, Q is D. If clock is 0, D remains the same. And so I'm going to code that. So library IEEE, remember, always start out with this. Use like IEEE dot standard logic, and then dot 1164 dot all, and then just Okay, now that we have our 4 libraries in here, let's get on to our next one. Our entity. And then for this entity, it's going to be a flip-flop. You can say D flip-flop if you want to, and then for ports here, you can see for what's coming in, it's going to be D and it's going to be clock. Those are both single digits as our inputs, so we can say just standard logic. And then for output, it's going to be Q. And then the output, we don't include Q naught, it's just the opposite of it. Standard logic. And then have your parentheses, then end the statement, end the entity, so end flip-flop. And then do the architecture, behavioral of flip-flop is, and then our behavioral flip-flop to begin the statement. Then remember, you always have to end the behavioral. These are just easy points to remember. And within it, what we're going to have is it's going to have a process, because whenever the clock, that's what we're going to be watching here. When the clock is positive as trigger, it's going to change the output. And so that's why whatever causes the output to change, we put in the process statement. So we're going to begin the process, and then we're going to end the process. And within our process, we can have an if statement. If you guys recall, oops, wanted to come over. Okay, so within a process, you can have if statements. If you're outside a process, you have to use when select or when, with select or when else. And so if the clock event, so the clock event means that, oh, the clock has changed like from 0 to 1 or 1 to 0. So if clock event and clock is equal to 1, that means it changed. And when it changed, I like a Lou diagram because I feel like diagrams help us a lot. When it changed, so this is clock event, it changed from like 0 to 1, or it could change from 1 to 0, but it changed to a positive value. So it was this positive edge right here. So that's what happened here. So if clock event and clock is 1, then Q, the output is going to be assigned D. So it's going to be straight from there. When it's the clock is 1, the output is the same as input D. However, if this is not happening, then D will stay the same. And so what we can do here, if D stays the same, we don't need to write anything. It just, because literally if I wrote else, D is D. I don't need that statement here. So I can get rid of that else because that's just repetitive. D is D. We only care about when the clock changes, then care about the value of D. Getting assigned, the output will be that value of D. Otherwise, oh, sorry, not, why did I say DD? Else it would be Q is Q. It would stay the same unless the clock event changes. Okay, so we end the if statement, and then we end the process, and then we finally end the behavioral. And so that's everything that occurs within our D flip-flop. And so that's the most important one. T flip-flop, who cares about it? If he asks, just reference your notes. Okay, now that we talked about that, let's get into the counters, because he said counters were part shift registers and counters. He said he'll test this on. And so I'm going to go through those. And then after those, we'll actually get into the more mealy and finite state machines. Okay, sorry. Okay. Hopefully you guys are doing well. Okay, let me clear all this. Okay, so for our, right before I do counters, because shift registers, we'll need to know those. A register is 2 or more flip-flops. And so a flip-flop stores 1 bit of information. And flip-flops, so like any amount of flip-flops here, so like 3 flip-flops, 4 flip-flops, store n bits of information. And so when you have more, 2 or more, that is called a register. So cool. Okay, so for a shift register here, what we need to know is at each active clock edge, content is shifted 1 bit position to the right. Bits are loaded in a serial fashion. And then, so let's do a 4-bit register. Those are the most common. And so when you have a 4-bit register, you need 4 clock cycles to load. And so what a shift register looks like, because we like looking at stuff, we have 1, 2, 3, and 4. Okay, and within this, we're going to have our, these are registers, our D flip-flops here. And we just talked about the D flip-flop, so that was good. And then here's going to be my Q, the opposite output. Then I'm going to have my D here, same here, Q, then opposite, and my D here, opposite, and then here I'm going to have my D, Q, then opposite. Okay, and then we need our clocks. So clock. Okay, sorry, just trying to make this fun. It's so not entertaining. Okay, so for our clocks, remember, for the shift register, you need an active clock edge on each one. You have to make sure it shifts at the same time. So you have to have it on the same clock edge, so they're all interconnected. And so we have all of our clocks here. And then they're all interconnected, like I said. So for our line, it's going to go from here down here. And then we're going to have our clock. So right here, I'm going to say clock. And then for the input, I like shift registers because it just shifts the input over one. So you just have the input to the first one. So here, the input comes in. And then when it occurs, this input goes to this one, and this output goes to the input of the other. This output goes to the input of the other. And then this one is where our final output is. So it just shifts it over once. You're literally going from this flip-flop, shifts it over here when a new input's in for the active clock cycle. Then it shifts over here, then it shifts over here. So it's just going to the right. So like to the right, and that's what you can think of with shift. Now shift, now shift, now shift, and do it again. Making this class a little fun, better than like when it's quiet and sad. Okay, so here is our output Q1. Here's our output Q2. Here's our output Q3, and here's our output Q4. Okay. Got all the outputs here. And so what I told you guys is literally it just shifts it one over to the right. That's what you need to know about a 4-bit register, how it works. Now let's talk a little about the parallel register. Because he wanted shift register, that means parallel register you need to know as well. So parallel register content is loaded in parallel. So do you guys remember the game Telephone? Telephone, as I like to think, it's going from one person, the information, and it's going to next, and then like you tell it to the next person, they tell it to next, and it goes down the line. It's like a domino effect. That's what I think of shift register as. But parallel register, it's sort of like you would tell that one person, but it just stays with them as the output. It doesn't go down the line. It just stays with them. And you have to insert it to every person individually. So you have to put the input individually to each person. And so it doesn't shift down a line. And so it's a little different. It's the opposite of a shift register. So, but you only need one clock cycle to load. And so this looks a little different. So you guys know, I'm going to draw out. It's just remember shift and parallel. They're opposites of each other. So 1, 2, 3. Okay. And now I'm going to draw out my lines here. And so what we're going to have is we're going to have information. Remember I told you guys how the info comes into each individual one here. So I'm going to have the info come in here, info come in here, info come in here, and info come in here. It has to go to each individual one. And so this would be D3, let's call it, D2, D1, D0. And then we have to have our output from each individual one. So Q3, Q2, Q1, Q0. Okay, let me make text. So Q3, Q2, Q1, and Q0. Okay, now we got all the outputs. Now let's have our clock. Remember how it's only one clock cycle to load in for all of them. What we're going to have here is for a clock, looks like 2, 3, 4. Let me draw down here, down here, down here, and down here. Okay, and now I'm gonna have it all connected. So, and then my clock. And then we're gonna have a reset, and the reset here, we're going to, you'll see, you can also have resets on here, but I'm just gonna include it on this one just so you have seen a reset, a clear before. So it's gonna be down here. And then I'm gonna call this a reset end. So flip it over, flip it over, flip it over, and down. And then this is going to be all connected because when you put in a clear, it's going to cause all the outputs to go to 0. Remember, clear, it reset, same thing. They're active low. Okay, so we have our clears hooked into all these. So I'm going to call it reset, and he likes to usually use that a lot. And we have our inputs going to each of these. And we have our outputs. So this is what a parallel one looks like. You only need one clock cycle to load, but you need 4 data lines here, you'll see. And that's the one thing about how parallel register works. You can put the information in parallel. It's nice you only need one clock cycle, where here it's 4 clock cycles for it to go from the very left to the very right. Because when you do one clock cycle, it moves over once, another one moves over another time, third time, then finally to the output for 4. And so that's the one nice thing about parallel is you get to see it immediately, but the shift, it takes 4 clock cycles to load it all the way down the line. Okay, now that we talked about that, that's good to know. Let's see, you can make the code from that. He gave the example of the code, so I won't go over that. I feel like just the general ideas. For our counters, we're going to talk about the ripple counter for the asynchronous, the 3-bit down counter, and we'll do the synchronous up counter 3-bit. And so we're going to talk about those 3 because counters was the last part he said for review. And then we're going to get into the other material. So let me clear this. So for counters, there's various types of counters we have. We have asynchronous ripple counter. We, for asynchronous ripple counters, then we also have synchronous counters. And so there's the 2 types you guys can use. So the difference between the 2, we're going to notice. I'm going to start with the asynchronous first. And so a lot of the times with counters, we have T flip-flops here. So good intro recap of what a T flip-flop is. So for these, use a T flip-flop. All the T's are going to equal 1. And the clock input edge triggered, and look for transitions on Q. And so for this, we're going to have a 3-bit up counter. So it counts up to 7. Watching low. Okay, so when I say 3-bit up counter, that means it counts up to 7. 0, 1, 2, 3, 4, 5, 6, 7. that is going to be 2 to the 3, which is 8 times. And then you can also say modulo 8, just so you know, that means it has 8 digits it counts it can go into. And so 0 to 7 is what a 3-bit does. And so for a 3-bit up counter, how it's connected, we're going to see it first, and then I'm going to walk you through how you can derive it real quick. So for a 3-bit up counter, let me make the diagram.
What did you mean by t equals 1 again? I think I missed it.
Oh, okay, that's for a T flip-flop. You're going to see it right now.
Okay.
So here's the first T flip-flop, here's the second, and here's the third. So remember, we have 3 flip-flops, we have 3 bits here. Okay, so flip-flop for each bit of information. And what we're going to have for the first one is right here, it's going to be 1. That's where the T equals 1. And then that's also connected right here. So let me put this up. Okay. T would be 1 there, and then T is going to be 1 here. So this is our T input right here. So T, and then our output, of course, is Q. And then down here, it would be the opposite. And then here as well, we have T. Output's going to be Q. And here we have T. Output's going to be Q. It's going to be not Q. Okay, we got all of our information. Oh, man, sad face. That's a little cut off, but whatever. And so then we have our clock. Our clock here, so you guys know, it goes to the first one, and then that clock is translated over, and you'll see why when I derive it soon. So that clock goes in here to the T flip-flop, and then the clock for the next is set actually by the naught, and then the clock here is set by the naught for this T flip-flop. And then our outputs are going to go here. So this would be our Q0, our Q1, and then our Q2. Okay, we got Q0, Q1, Q2. And for this, what it's going to look like in our truth table, okay, here we have Q2, Q1, Q0. Then we're gonna have our count. Okay, so if we are counting up, it's gonna start at 0, 0, 0, makes sense. That's gonna represent 0. If we keep going 0, 0, 1, that's going to be 1. We have 0, 1, 0. It's going to be 2. If we have 0, 1, 1, that's going to be 3. We have 1, 0, 0. That's going to be 4. We have 1, 0, 1. That's going to be 5. We have 1, 1, 0. That's going to be 6. 1, 1, 1. That's going to be 7. Remember, we count up 0 to 7. So let me just move this over, make it nice and neat. Okay, so we have our count here, 0 to 7. We have our inputs here. Sorry, disorganized. Okay, there we go. That's better. Okay, so there we go for all of our values. And what we're going to do is we're going to look specifically at how these change and why it's set up this way. So for on this one, we're going to notice that Q is 0. I'm going to draw this in one color. It changes literally every single one. So on every clock edge, it's changing 0 to 1, 1 to 0, 0 to 1, 1 to 0. And so what I'm going to write here is Q0 changes at every clock edge. And so for a Q0, though, you notice what's going to happen is that's why we have, oops, every clock edge. That's why Q of 0 is set equal to the clock. And so then let's try the next one. So Q1. Q1 goes from here. So let me 0 to 1 here, and then goes 1 to 0, then goes 0 to 1. So that's where it changes. And we notice on Q0, that's where this goes 1 to 0. That's where this goes 1 to 0, and that's where this goes 1 to 0. So Q1 changes when Q0 goes from 1 to 0. However, this is a positive edge triggered clock. Look at the inputs. They're positive edge. There's not a bubble before it. Therefore, this needs to change. So we're going to say Q1 changes when, and then the not at Q0 goes to 0 to 1. And so that would be a positive trigger. And so that would cause, for a positive edge trigger clock here, we need a positive edge trigger starting that clock, not a negative edge trigger. Therefore, that's why we use this one here. We use the negative as our input for the clock here. Because it's a positive edge trigger, we need a positive edge trigger for the input. So that's why we have to use the not Q as our input to the next clock. Okay, let's look at the next one. Here it goes 0 to 1, and that's the one change we see. And if we were to start again, it would start at 0, 0, 0, correct? And this would be 0 here. And we notice Q1, that's when it goes 1 to 0, and then it goes 1 to 0 again. So looking at that state, so let me write this here. Q2 changes when, and then Q1 goes from 1 to 0, but that's negative edge trigger. So actually Q2 changes when the not of Q1 goes from 0 to 1. Okay, and so that's why we have the not of Q1, and that's giving us the clock input for Q2. Okay, now that we talked about that, we looked at the states. The 3-bit down counter is, it has the T's all connected. The only difference with the 3-bit down counter is that the Q output is connected actually to the clock, not the Q not. And so the reason being is if you do the state table again, you'll notice that it actually toggles on the positive edge trigger here. And so that's why the Q is legit connected just to the clock of the next one, Q to the clock of the next one for the down counter. So that's the nice part of it. And so you can just derive that on your own. The only thing you need to memorize, not memorize, sorry, know is this is for not, I'm going to draw it in green. It would go in here, and then this one would go in here. And then you wouldn't have this line here. And hopefully that makes sense. And that would be for a down counter. Okay, now that we've done that, let's get to our next one, which is the asynchronous up counter. And for the asynchronous up counter, I'm gonna erase all this real quick. For the synchronous up counter, sorry, because we're talking about asynchronous up here. So synchronous up counter, so let's do example, 3-bit up counter. The interesting part about these is the T is not for all the flip-flops. So we still have 3 flip-flops because we have 3 bits. 1, 2, and 3. The difference being with all these flip-flops, so here I have my T, then here I have my Q. Yay, it's Christmas colors. And then here we have the not. Okay, here we have the T, Q, not Q. And we have the T, and the Q, and we have the not. Okay, and within this one, we're gonna have the clock actually connected to all of the clocks. So that's The reason it being synchronous is because it's synced with the clock in this one. The asynchronous is not synced with the clock because the cues determine the clock inputs for the next flip-flops. But here the flip-flops are all connected to the clock. Okay, so I'm going to draw it here, going here to our clock signal. And using the triangle, we're going to have triangle here, triangle here, and triangle here. Okay, we have the 3 flip-flops and we have the T's going to each one. And we're going to just have the 1 go to this one. And you're going to notice that, let me just make this Q0, Q1, and Q2, make it easier to understand the outputs. So here, it's going to connect to T. You'll see Y. And then the AND gate is going to have Q1 connected to as the next one. Okay, so let's figure out why I just wrote all this. And so if we draw a truth table, exactly the same as the last one, we have our Q's on one side and we're going to have our count on the other. So we're going to have Q2, Q1, Q0, and we're going to have count. So I'm going to have 0, 0, 0, and for my count, that's going to be 0, 0, 0, 1. For my count, it's going to be 1, 0, and 0. Okay, now we got our count from 0 to 7. Now that we talked about that, we're going to go and we're going to count all these. And so what we're going to have is the Q. Let's look at what happens. So for the Q0, you notice it changes every single one. So what I want you to do here is look at the states, don't look at the transitions. So the state value right here, let me circle it. We have our 1, and then it changes again from 0 to 1, and then changes again, and then changes again. And so it's flipping literally every single time here. So Q0 toggles every clock edge. Therefore, what we do is we're just going to set T equal to 1 because we focus on the state value. So what we're going to have here is we're going to have T equal to 1. And so that means it's going to toggle every single time. So every time the clock hits, it's going to toggle. Because notice here, it's toggling. It's going from 0, 1, 0, 1, 0, 1, 0, 1. It's toggling. So every time it's going to toggle when the clock input is active. And then for our next one, we're going to look at the state values in the synchronous counter. So here, what's going to happen is we're going to notice that, look here, we have our 1 here, and then it's going to have another 1 here. And so it toggled, see here, oh, sorry. It toggled here every time T was equal to Q0. You notice it's toggling. It toggled here once when Q0 was 1, it toggled this. When Q0 is 1, it toggled and flipped to 0. When Q0 was 1, it toggled to 1. And then here, when is 1, you'll notice that in the next one, it's going to be 0, 0, 0. So it will toggle this to from 1 to 0. So that's why we connect Q0 here to the input of the next one. Since Q1 toggles every single time Q0 goes to the high state. So we're going to see, I'm going to write this out in terms because it's a little confusing. So we notice Q0 toggles every single time. So toggles every clock edge. So therefore, we set the toggle equal to 1. So when the clock edge occurs, that's when it toggles. Q1 toggles when Q0 is equal to 1. we notice. And so that's why we say T is equal to Q0. And we notice Q2 toggles when Q1 is going to be equal. We'll see when this occurs, toggles here, you'll notice. Oh, oops, let me get a different color. So toggles here. And that's when we notice that it went from 1 to 0 here, but focusing on the toggle state, it's when this one was 1 and this one was 1, it toggled here. And we'll notice when this one's 1 and this one's 1, because our next state is going to be 0, 0, 0, the Q2 value will change from 1 to 0. So it's when Q1 and Q0 are both 1. So here I'm going to write when Q1 is equal to 1 and Q0 is equal to 1. Okay. Now that I wrote that, that means the T is equal to Q1 times Q0. Okay. So that's why here I had the AND gate between Q1 and Q0. And so that's how we make our up counter for the synchronous. Okay. Now that we talked about that, I want to discuss, I think that should be good for a non-modulo counter. That one might be on it, so let me talk about that. There's parallel capacity, but I'm gonna skip that one. I don't think he can test us on that during the exam time. So let's go to the non-modulo counter, and that should be our last counter. And then we finally are going to get into all the other material that he might test us on from chapter 8. Okay, so here's our counter. So we have our up, and this is when clock input attached to T flip-flops. Okay, so for our non-modulo 2n counter, what this one's going to be is, if you think of like 2n, like it's usually like 2, it can count up to, it could be 2 to the n, and then usually when we have a 3-bit counter, it counts 0 to 7, a 2-bit counter, it counts 0 to 3, a 1-bit counter counts 0 to 1. And so that's our non-modulo. Let's say we want to count up to 5. Well, how are we going to count up to 5? The lowest we can use is the 3-bit counter, which counts up to 7, because a 2-bit counter only counts up to 3. So therefore, we have to use a 3-bit counter. So let's say we want counts up to 5. And so then load in 0 to the counter at the next turn. And so we're going to count up to 5 because that's why it's non-modulo. It counts up to a number that's not like 7 for the 3-bit, 0 to 7, 0 to 3 for the 2-bit. And then so we're not counting up to a number. So that is already at the end of that bit storage. So what we're going to use for this is we're going to use a synchronous counter with parallel loading. That's what you use a lot of times because you can load in the values when to reset it. That's why. Okay, so for this, when we want to count up to 5, it's going to look something like this. So I'm going to have my Q2, Q1, my Q0, and then here I'm going to have my count. So I'm going to have 0, 0, 0, 0, 0, 0, 1, 1, 0, 1, 0. Okay, then we go to 5, and then finally it resets at 0. Okay, there we go. Okay, so when we count, when the count reaches 5, then we're going to make the load equal to 1. And so that's when Q2 would equal 1, Q1 would equal 0, and Q3 would equal, or sorry, Q0 would equal 1, because that's the value for 5, 1, 0, 1 in binary. And then, so load would equal to Q2 times not Q1, and then times Q0. And then Q2, if we notice here, just the reason I'm saying that, that's literally just here for value 5. Q2 is 1, Q1 is 0, and Q0 is 1. At that 5, at the next, when you hit that number, then you're going to reset to 0. So that's why for a load, we set it equal to 5. So once it hits that, then it's going to reset it. And so we notice we can simplify that because look, that's the only time Q2 is 1 and the only time Q0 is 1. So we can simplify. We can take out this Q1 term real quick, make it a little simpler. And so our load is equal to Q2 times Q0. Okay, now that we have that for a load, what we can draw then, what it's going to look like for a counter is here, and we're going to have our enable to count. We're going to have D0, D1, D2, D3. That's our parallel. Oh, sorry, stops at D2 because we use 3 bits. That's our parallel inputs. We're going to have a load. That's when to reset it. And then we're going to have our clock input. On the right-hand side here, we're going to have our Q0, Q1, and then Q2. Okay, and then what we're going to have as our inputs here is we're going to have, for a load, let's do that first since we know the equation for it, Q2 and Q0. So I'm going to have my Q0 go over here. And then I'm going to have my Q2 come over here as well. And we're going to AND these two together to the load. And then after we AND them, the clock is going to be connected, of course, to clock because we're using a synchronous counter. So the clock input is attached. And then for our enable, it's going to have to be 1 to count. For parallel inputs, that's going to be what we're going to input in here. So it's going to start at 0, 0, 0, correct? So that's why I'm just going to put in as a starting parallel input value. And then our outputs, we're going to get our Q0, our Q1, and our Q2. Okay, now that we've covered all that, that's how you design a non-modulo counter. And so we talked about the most important counters. And now let's get into the actual more in Mealy finite state machines. So let me clear this. And let me clear all this info off here. Okay. So this is where we're actually going to get into all of our new stuff. And so for the more in Mealy type, we're going to have a fair amount of info on these two. And so we're going to divide it to make it make sense. So remember when we talk about combinational circuits, the output depends on the present inputs. Sequential circuits. Outputs depend on past as well as present inputs. And then this, for those past and present inputs, you're going to use flip-flops and combinational flip-flops and combinational logic. And it's also called the finite state machines for these, also called finite state machines. Okay, so what we're going to see here is the general form of a finite state machine. And for a general form, we're going to have 3 blocks. 1 here, Mhm. And we're gonna have our text input. So for the first one, it's a combinational circuit. Here, we're gonna have our flip-flop in between, and then we're gonna have a combinational circuit here. And so this is what your finite state machine looks like. And you're gonna have an input and an output, of course. So within our combinational circuit, we're going to have our input. So usually that's W. And then it's going to go to the flip-flop. These are D flip-flops in here. So that's going to go to D. And then we also have a clock. Remember, those D flip-flops have a clock input as well. So we're going to have our clock. And then the Q is the output that goes to the combinational circuit here. And then we're going to have the output is going to go back, we're going to see, to this combinational circuit. So it goes back here. We're going to see an example why that occurs. And we're going to also see our output Z from the combinational block, this last one here. And for Mealy types, what we need to recall is that the input also goes here to this combinational circuit at the output. And so this is for Mealy type. We're going to see it depends on the present input as well. So for Mealy's, that's where it's located. And so what we're going to see here is our combinational circuits. We have one at the start and one at the finish. They depend on the present inputs here. So depend on the present inputs, depend on the present inputs. And then our sequential circuits is we have flip-flops in combinational logic. So that's where we have this middle block. This is when we have sequential circuit. So we're going to have combinational circuits as well as our flip-flops, and this is what composes our finite state machine here. And so our W is our set of inputs, our Z is our set of outputs, the Q is going to be our flip-flops in here for states. The flip-flops are edge triggered, so only one state transition per clock cycle. Our Moore type, the output depends only on the states, where the Mealy depends on both inputs and the states. So our Moore is only the states here from Q, but our Mealy is also Q and the inputs that we put to the combinational circuit in the beginning. Okay, now that we talked about that, we need to talk about the synthesis of a finite state machine. And so this is going to be very important. I'm going to run through one example of a Moore type, and then I'm going to run through one example of a Mealy type. And then that should be pretty good. So let me do those. Clear this. Okay. So for synthesis of a finite state machine, you're going to start with the description. You're going to go to the algorithm. Then you're going to go to the state diagram, and then go to the state table. And finally to the circuit. Okay, so we're going to do an example here. It's always good to review. So for our example, it's going to be based off the input W, and then we're going to have our output Z. So example is going to be a sequence detector, and we're going to have one input W, and then one output Z. And then if W is equal to 1 during the immediate 2 preceding clock cycles. And so when I see this, the previous clock cycles, it doesn't change instantaneously. We'll see, so it's not Mealy. That's what I know. I'm sort of inferring that already. It's going to be a Moore type. Z equals 1, else Z equals 0, because it just doesn't change on the second state. It's the previous ones, and then it changes. Okay, so I'm going to show you guys. So here's our W, what we have for it. It's going to be 0, 1, 0, 1, 1, 0, 1, 1, 1, 0, 1. For Z, it's going to be 0, 0, 0, 0, 0, 1, 0, 0, 1, 1, 0. Okay, we got both right here. Now what we need to do for our description here, that's what we start off with first. Start with the description. Assume the starting state. Remember, you always have to have a reset after reset is called state A. And with z equals 0, and then also transition between the states, we know, only occurs at the active clock edge. Okay, now we need to do the actual algorithm. For the algorithm, that's where we're going to be in state A, and then we're going to see there's literally, because it's a more type, we know from here, this is how I can tell it also. See how the first, do these line these up better? There we go. Okay, so see how Z is 1 when the preceding 2 are 1, Z is 1 when the preceding 2 are 1, and then Z is 1 here when the preceding 2 are 1. So it depends on the previous 2 in order for Z. And so what we have here is in state A, Z is 0. So that means we have no pattern right now, because this is where, or sequence. And so within state A, if W is equal to 0, remain in state A. If W is equal to 1, go to state B. Reason being, state B is going to be the second check to see if it's another one. So in state B, Z is still equal to 0. There hasn't been 2 consecutive 1s yet. So if W is equal to 0, go back to state A. However, if W equals 1, go to state C. And then at state C, that means W was 1 both times. 1 here to go state B and 1 here to go state C. So Z is equal to 1. The two inputs before were both 1. So that's why we can set Z equal to 1. So if W equals 0, go back to state A. If W equals 1, remain in state C, because that means it's just another 1. So it's then the previous 2 would be 1s, and so you can stay in here. So the state diagram, I feel like, explains it better. So your state diagram, what that's going to look like is, let me do it here. So for the state diagram here, we're going to start. So let me do our circles. So we have state A here, we have state B, and then we have state C. And we have a reset. So here, reset N. And that's going to go into state A here. And A is where Z is equal to 0. Here's where B is, and B is where Z is equal to 0. And then C is going to be where Z is equal to 1. Okay, so I just copied that over from our algorithm. And so at the reset N, when you press reset, it starts at state A. So if W is 0, remain in state A. So here is where W is 0. And then if W is 1, you're going to go to state B here. So W is 1. And then if W is 0, you go back to state A. So W is 0 here. And then if you have W is 1, then you go to state C here. And then if W is 0 in state C, you go back to A. So W is 0. But if W is 1, you remain in state C. And that's how you draw your state diagram. So now that we talked about the state diagram here, we're going to have to look at our state table and then the state assigned table. And so for our state table, we're going to have 3 present states. And so let me show you guys how to draft your state table. So here, let me do state. And for your state table, what it's going to look like is you're going to have the present state, you're going to have the next state, then you're going to have the output. And then we're going to draw 3 columns here. 1, 2, 3. And then for our present state, it's going to be these states here, A, B, and C. We have only 3 states, so A, B, C. In our next state, so you guys know, is W0 or is W1? That determines the next state. So in my next state here, I'm going to say W0 or W1. My output is Z. And so Z either is going to be 0 or 1. And so let me do it here. So when W is 0, our next state from A, we just remain in A here. So that's why I'm going to write here A. When W is 1, we go to B. Down here, when W is 0, we go back to A. When W is 1, we go to C. When W is 0, it goes to A. When it's 1, it stays in C. And so what we're going to have here is when you're in state A, remember, look inside here, it's 0 as our output. When you're in state B, it's 0. And when you're in state C, it's 1. Okay, went over a state table. Okay, now we go to the state assigned table. Yay. For a state assigned table though, let me go back and mention these few things real quick before we start out with it. Good note taker. So if we have one flip-flop, you got to remember with one flip-flop, that means we have one state variable and realize 2 states. So 0 and 1 are 2 states. And so we have 3 states here, A, B, and C, right? And so we need 2 state variables because then that can handle 4 states. We're going to have 1 unused state. So that's going to be 2 state variables. And so 4 states. And so 1 unused state here. And then, so what we're going to use is we're going to have lowercase y1 and y2. Those are going to be the present state variables. And then capital Y1, capital Y2, those are going to be the next state variables. And then what we're going to do is for this, because we have to declare what each one's going to look like in our table, since we have 4 states, I'm going to just use the values 0, 0, 0, 1, 1, 0, 1, 1. Okay, and so 0, 0 is going to represent state A. 0, 1 is going to represent state B. And then 1, 0 is going to represent state C. Cool. And then this one's just going to be the unused state. And so what's going to happen here is when we're going to now make our state assigned table, literally we just plug in what we did here in. So we just plug in 0, 0 for A's here. We plug in 0, 1s for B's and 1, 0s for C. And so let me draft the table here. So let me put this. Okay, let me move this over. Okay. So for my state assigned table, we can put it here. Okay, we're going to have our present state. And remember for that, that's y1, y2. We're going to have our next state, which is the capital y1, y2. And remember, our next state is dependent on w0 versus w1. And then therefore, we can say y1, y2, and then y1, y. Sorry, y2, y1 going down from the most important. Y2, y1. And then here we're going to have finally the output, which is going to be z. Okay. We got all those. Now I'm going to draw the table just like the others. So here, have our present states, have our next state, and our outputs. So the output column will have our 0, 0, 1. And then for A, we had 0, 0 representing it. So wherever there's an A, I'm going to put 0, 0 here, 0, 0 here, and a 0, 0 here, 0, 0 here. And then for our B, we're going to have 0, 1. And so that's going to be 0, 1, 0, 1. And then for C, it's going to be 1, 0. So 1, 0, 1, 0. Oh, and 1, 0. Okay. And then now, remember, we have an unused state. So just to make sure about that, you're just going to put in 1, 1 here. And then literally, it's just don't care about that unused state. So just recall that you have a don't care condition for the unused state. Makes sense. When you don't use it, you don't care about it. Now we're going to, the next step after the state assign table. So we went through, recap real quick. Started with our description. So that was all this part here, where we have the pattern. So we assume the starting state after reset is A with 0 for Z. Transition between the states only occurs at the active clock edge. And then we have our algorithm. The algorithm here is in state A, in state B, in state C. State diagram here looks like this. And then we have our state table here. And our state table is where we have all of our states, what's going to happen. Have our state assign table then. This is where we just put in our values for the A's, the B, and the C state. And then remember, you have your lowercase y's for the present state. Oh, sorry, Y2 should be on the left here. And then you have your uppercase here. And then you have your output. And so let me just, finally, we're going to talk about the actual circuit. And the circuit we'll need to make equations from in order to know how to build it. So from this actual state assign table, we're going to make our equations from this. And so let me erase a little what's on here. So I'm just going to clear. Let me try to erase some of that. Okay. So now we're going to make our circuit. And so what we need to do is with our state assign table here, we need to get an equation for Y1, Y2, and also Z, our output. And the reason being is Z, of course, we need one for the output, and the Y1 and Y2 are going to be outputs of the first combinational circuits. And because we need to know for next state, so I'm going to create a truth table here. So our truth table. And let's start with our Y1 and Y2. So right here, lowercase y2, y1. And it was up here. Y2, y1, sorry. Okay. And then also we're going to have our W as our input. Remember, for the first combinational circuit, we have an input. And then we have Y2, Y1. Now that we're doing that, we're going to organize this up. And so it's going to start at 0, 0, 0. And then let's keep going. So 0, 0, 0, 0, 0, 1, 0, 1, 0, 0, 1, 1, 1, 0, 0, 1, 0, 1, 1, 1, 0, 1, 1, 1. Okay, and then my Y2, Y1. If we're looking at this, and this is what I'm seeing for the first one, 0, 0. Sorry, change color. 0, 0 here. That's 0, 0 here. W 0 right here. So that means this one right here because it's 0, 0, 0. So my output here is going to be 0, 0. And then let's look at the next one, 0, 0, 1. Same thing, 0, 0, but this time it's 1 here for W. So it's going to be this one here. So it's going to be 0, 1. Okay. Now let's just go down the entire line. So it's just literally left to right here. So how I wrote it. So 0, 0 is next one, 1, 0, then it's 0, 0, then 1, 0, and then DD and DD. Okay. Now that we got the truth table, we're going to have to put y1 in terms of y2, y1w, y2 in terms of y2, y1w, and then we're also going to have to find z in terms of the present states, lowercase y2 and y1. So what we're going to do is we're going to make a k-map for this y2, and we're going to make a k-map for this y1 to get the equation for them. And so let's make our k-maps. And so y2 here. Okay, I'm going to have y2, y1, and then on this side, I'll have w. Okay, let's go 0, 0. Let's go 0, 1. We're going to have 1, 1. We're going to have 1, 0. 0. Okay, let's divide this up. Draw out our map. And so when we draw this out for a big Y2, what we're going to do is we're going to notice, fill in the values here. So for 0, 0, 0, what we got was 0, 0, 0, 0, 1. That was 0. Here it is 0. And then we had here as 1. So you're literally just taking these values here. And then we had, remember, it cuts it off. So here it's going to be 0. Down here it's going to be 1. And then we have our don't care, don't care. Okay, now that we got that truth table form, let's collect our terms here. And so we notice in the bottom where sadly nothing's going to go nicely. So we're going to collect these two right here. And then we're going to collect these two right here. With those collections, what you should get for y2 is it should be equal to, looking at this, y2 doesn't change, y1 stays, sorry, y2 changes, y1 stays the same, w stays the same, and then plus, and then the other one would be y2 stays the same, y1 changes, but w stays the same. Okay, we got that. And you can actually simplify this a little, take the w, and then have y1 plus y2. Yay! Okay, and now for y1, what we're going to do is we're going to do the exact same thing. I'm just going to give you the equation to speed it up. Y1 would be equal to w times naught of y1 times naught of y2. And then for your z, how you're going to do that, it's a simpler table here. And that's the nice part about this is for your z, what's going to look like is it's going to have the z on this side, and then you're going to have y2, y1, and it's going to start at 0, 0, 0, 1, 1, 0, 1, 1. Okay, and then here you're going to have 0, 0, 1, 3. Okay, and that's literally just taken from this column and this column here. This truth table was taken from this column, and then we took down this column from left to right and going up to down. And then what we're going to form for a K-map here, it's going to look something like this. And then we're going to have our 2 columns, 2 rows. And then here, it's going to be Z. And then we are going to have our Y2 up here. You start with the largest one, then our Y1 down here. And then we're going to have 0, 0, 0, 1s. So when I do this, 0, 1, 0, 1. What we're going to see for 0, 0, it's 0, 0, 1, it is 0, 1, 0, it's 1, 1, 1, it's D here. Okay, so we can form the equation. Luckily, this D combines with this 1. And so what we can do is our simplified equation is Z equals, and it's Y2, lowercase y2. Okay, now that we got that, we got our equation for y1 here, got our equation for y2, got our equation for z. Yay! Okay, we got all of our equations. So we got y1 in terms of y2, y1 and w. Got y2 in terms of y1, y2, y and w. Got z in terms of y2, y1. Hey, now that we got that, we can form our circuit. And so let's draw out what our circuit's going to look like. And so now I'm going to just clear this up here. And so take out this. Okay. Circuit diagram. And so for our circuit diagram, now that we got this process done with all the equations written, what's going to look like is, remember how I told you guys you have two combinational blocks and then you have a flip-flop block in between. So combinational block, flip-flop block, and then combinational block. Okay. And what we're going to have as our inputs is, remember how I told you guys you're going to have W as an input to the first combinational block. And then I'm just going off memory. What happens in here goes to here, and then what happens in here goes to here. And then we remember the output connected back to the input, and it's not mealy, so the input doesn't connect to the output. So, okay, and that's what I recall. We're going to have our, remember this truth table, it's also y1 and y2, so we're definitely having 2 here. So we have 1 here, and then this is going to produce 2, because this would be our uppercase for next state. So y2, y1, and then I have my lowercase y2, y1 here. So what's happening is I have those two. I'm looking at my truth table here. I have y2, y1 in W because I had to have those. I have my input W, and then I have my y2, y1 going back here for my lowercase. So those are going to be the inputs here for my combinational block, and those produce the outputs, the capital Y2, Y1. So that's why I have them here. And so I need to connect this one as well. That's why I'm not an artist. I would be terrible and be broke if I went into art as my major. Y1 here, and then I have Y2 here. And so now that I have those, inserting into this combinational circuit, I have these next states, capital Y2, capital Y1, and then I also have lowercase y2 and y1 here. And then it's going to go for this combinational circuit, and it's finally going to produce the output Z, which we want. So that follows everything here in our state assigned table, because when we made our truth table, it was based off lowercase y2, y1, and w, and it produced then the next state of capital Y2, Y1, and then it goes through the flip-flops, and then that determines our present state. And then our output from this entire finite state machine is Z. And so now that we have done that, we're going to have our flip-flops in here. So I'm going to draw my two flip-flops, one here and one here. And we're going to have our clock input going to those flip-flops. So my clock going to this one here is going boom in here, and then we're going to have a clock in here as well. And then the Q is going to be Y2 here, Q is going to be Y1 here. And so that's, sorry, my D, because these are D flip-flops. And then the output produced is going to be Q, then Q here as well. And now this is where I'm going to be using my equations. So we're going to see that Z is equal to Y2, it said. So literally just connect it right there. And then, so this equation checked off. Let's go to capital Y2 here. So it's going to be W. And so we're going to have W here. And it's going to be also, or that anded with Y1 and Y2 ORed together. So I'm going to OR these two together. And then that's going to and with this. Go to Y2. Okay, now we're going to do this capital Y1, which is W, and then the naught of Y1, and then naught of Y2. So let me do that in a different color. So we're going to, interesting or not, there's a simpler way to do this because Dr. Koo told me, and he was like, you don't want to use more logic gates than you have to. So good point to bring up, guys. Right here, we notice we already produced the invert of Y2 and already the invert of Y1. And so going back here, remember, these are connected right here, but remember Q naught here. So that would be Y2 naught. We can connect this back. Let me jump it here. Let me just insert it on the other side, actually, make it more easy. Okay, so connect it back here. Yeah, I'm just gonna have it here. So this would be Y2 naught, lowercase y2 naught. And so then we're going to have that. Sorry, there's just a lot happening in here. And then this is going to be our Y1 naught. So our Y1 naught, we're going to have it. I'm just going to draw it for here. It doesn't intersect any of those. It has no connection. And so then the Y1 naught is going to be here. So that's our Y1 naught. And then it's connected with W as well. So we're going to have our W2. And then it's going to be and together. And goes through here. Okay, so we got those all ANDed together to produce our Y1. That's good. Got our Y2 as well. Good. And we got our output connected. So we are good, everyone. That's what we have. So I guess here for Z output, I can actually, the Y1 only went right here to this one. Right there. Okay, so that's what we did, everyone. We got the 3 equations for the Moore type. So good job. Now let's look at a Neely type. Similar process. So it takes a little while, but you guys get it. So let's go here. At least it's not all the counter knowledge. Once you do it and you practice it enough, it comes very easy. And so you can do an alternate assignment because we had an unused state that would just produce a different output, which might be simpler. However, you don't need to worry about that. Okay, so there's coding for this Moore type. And for this Moore type, what it codes off is those state transitions we talked about. So let me just go over that behavioral coding because he probably will ask us on there. I'm just going to do one type because you can code however you want. And so let me pull it up here. VHDL code for a Moore type finite state machine. So let me erase everything on the screen right now. Okay, you guys remember the diagram we had here? A, B, and C. Okay, so what we have for A is going to be Z is equal to 0. B is going to be Z is going to be 0 as well. And C is going to be Z is equal to 1. Okay, and remember reset N here, it starts at A. W is equal to 1. When W is equal to 0, keeps repeating here. When W is equal to 0, goes back to A. W is 0 went back here. When W is 1 went here. When W is 1, it stayed here. We just W 0. So this was just from the last problem we did, recounting what happened. W 0. I'm sorry, no. W is 1. Okay, W 0 here. W is 1. 1. W 0. Okay, here's our diagram. We have all of it, so let's code the behavioral. So VHDL coding is what we're going to focus on right now. This is the one I would use on the exam. Your coding question is going to be the longest, so you know. And so when you hit the coding question, spend, I think you get 20 minutes per question. I took like 25 minutes last time, and then I spent 35 on the rest. So that's definitely your longest one. So when you hit that one, it was my first question on the exam, and I was like, oh shoot, but then did fine. So just start on the coding one, make sure I have 25 minutes for. Standard logic 1164 dot all. Next one is use IEEE dot standard logic and arithmetic, and then dot all. Then use IEEE dot standard logic, and then unsigned dot all. Okay, entity. And for this one, For entity, I'm gonna just call it more type. Is okay, I'll just say more is. And then for this, what you're gonna do is for ports, if you remember, there's a clock that goes into those D flip-flops in that middle stage of the, because we have the combinational circuits on the outside, but we have the flip-flops on the inside for finite state machines. We have a reset N that goes to those D flip-flops as well. And we have a W input that goes to the first combinational block. And so those are going to be our inputs, standard logic. And for our next one, we're going to have our output, which is Z. So that will be our output, and that's standard logic. And then just remember, then you're going to end your entity, so end more architecture. Behavioral of more is, and then we use behavioral because this was all written in that truth table, so that's why we use behavioral. So we're going to have a template. The first thing we focus on is state transitions, and then the next one we do is we focus on the Z output. Okay, so this is the most important 2 lines of your code right here. Type, state type. So make sure you just have these written down somewhere, is ABC. And make sure you have commas in between to separate the state types. And then your next one is signal Y state type. Okay, so we declare Y as a state type, and then our state types are A, B, and C. So here we declare Y as a state type, and then part of that state type is A, B, and C, because that value can change. And so what happens here is we have 3 possible states, which are A, B, and C, and then the signal Y, if we remember, that's our present state, the lowercase one, and that in it, the uppercase is the next state. It's assigned to those types. And so we're going to begin the process of this behavioral. So right here, I'm going to write begin. And to begin it, we're going to begin the process. It's a process statement because if there's any change in the clock, positive edge triggered, and if reset and asynchronous have to be up there, we're going to begin the process. And when we begin the process, if reset n is equal to 0, then, so if reset n is equal to 0, then our outputs are all going to, remember how on the chart, reset n equals 0, we go to, our current state is going to be A. So that's when we set y to A. And so then else if, so you do asynchronous signals first, else if clock event and clock equals 1, then, and then here it's going to be a case statement. Case of y is, and then when A, and then that's going to be if W is equal to 0, then Y will be set equal to A. And then else Y will be B. And then end if. Okay, so what happens here is when you're in state A, so for the case for Y, so our present state, if you're in A, so right here in this A circle, if W is equal to 0, then you stay in A, but if it's not equal 0, then that must mean W is equal to 1, so you go to state B. Okay, next one is going to be when B. Okay, so when B, we're going to assign if W is equal to 0, then Y is going to be equal to A. If else, Y is going to be equal to B, state B. And then end if, then when C if W is equal to 0, then Y is going to go to, and then here, if W is equal to 0, Y will go to A, and then else Y is going to stay in C. And if, okay, we ended all these ifs here, then we have to end the case. Then we have to end this if statement here, this large one we're in. Then we have to end the process. Then we're going to end the behavioral. Okay, now we got all that done with, and that was our code. However, that was only the state transitions. We have to assign the output Z. So right here, everything here, perfect, perfect. We did everything correct. So right here, it's all 100% good. The error we made was that we just haven't talked about the Z output. So Z is going to get assigned to 1 when, because remember, we're not in a process anymore, so we can't use if statements. We have to use either the when, else, or the with select. So Z is going to be 1 when, and then this would be Y is equal to state C, else Z would be 0 when else, yeah, we just need to say else 0. And then remember, I have to end it with a semicolon, and that will be for Z, and then we are good. We assign the output as well. So those are the two major parts. You have to do all the state transitions within this diagram here, the state diagram, and you have to do the outputs. Okay, that goes over everything there. Talks about all that VHDL coding. There's some one hot encoding. I don't think he'll test us on that. Now the mealy type we'll get into, and then we'll just do all my homework problems. I'll just show you what I did for the homework problems so you guys know how to do it. Partitioning, I feel like you guys understand that probably pretty well, so I don't think I need to cover that unless someone wants that, and I'll do that instead of the homework problems. But I thought you guys probably want to see the homework problems done correctly, what they should look like. So that might be a better option. Okay, so let's get into the mealy type, everyone. Okay, so mealy finite state machine. Okay, remember, we start with the description, everyone, what we want happening. Then we go to the algorithm, what each of those states are. Then we go to the state table, or sorry, state diagram. Then we make our state table, which is also the state assigned table. Then we do, finally, the circuit. Okay, we got that all good. So here, what we need is, we're going to, remember, mealy finite state machines, they have, the output depends on the present states and the input. So what we're going to have is this sequence detector. It's going to be Z equal to 1 in the same clock cycle when the second W equals 1 occurs. Okay, so for the sequence detector, what's going to happen is, let's look at what it looks like. So if my W here, I'm going to just show you guys an example in Z. Always write out the combination so you can see it. So let's say, so right here, Z equals 1 in the same clock cycle when the second W1 occurs. So right here, 2 1s occur, same cycle. Here, 2 1s occur in W, so same clock cycle, 1 as an output. Okay, now that we talked about that and we did all those, that's our description here. So for our algorithm, make sure to assume that state A as the starting state. So that's where reset is. Reset n. Okay. And so in state A, we don't put the outputs here, but if W equals 0, go to remain in state A. So remain in state A. But if W is equal to 1, go to state B. Okay, in state B, if W is equal to 0, oh, sorry, I forgot. Sorry, guys. You have to assign the outputs with these because the output is dependent on these inputs right here. So if W is 0, remain in state A, that means it's 0 still. Right here, it's Z 0. The only time Z is 1 is when the second W1 occurs. So if W is equal to 0 here, go to state A because that means no longer sequence. So Z would be equal 0. However, if W is equal to 1 here, remain in state B. And that would mean Z is equal to 1 because you had a 1 here and you had a 1 here. 2 ones in a row, that causes the output to automatically be 1. Okay, we only needed 2 states. So that was very nice. So now let's do our state diagram here. Okay, for state diagram, what we're going to have is we're going to create our circle. So we're going to have A here, we're going to have B here. And then we're going to have so let me label these. So we're going to have state A. We're going to have state B. W is equal to 0. Go back here. If W is equal to 1, go state B. We're going to draw this. So for the drawing, if W is equal to 1, remember we stay in state B. W is equal to 0, you stay in state A. I'm going from up here, just copying that honestly over. And then reset N. When that occurs, you're in state A. Okay, here's our state diagram. Now we need to do the state table. And
Don't
first,
don't we need the Z value
yes,
on the lines
yes,
as well?
you're correct, John. Thank you.
No problem.
Okay, so John Smart here. Z is equal to 0 here. And then, so you can just put a slash here. And then down here, Z is going to be equal. So we had a 1, and then Z is equal to 1 here. And then right here, Z is going to be equal to 0. And this one up here. Okay, and so this is what our state diagram looks like. And now we're going to have to go to the state table. Okay, for state table, what we're going to have here is we're going to have present inputs, present states, next states, output. And so present state, next state, and our output. Present state is going to be, remember present is the lowercase y2, y1. Let's look here. We only have 2 states actually. If we only have 2 states, remember what I told you guys? You only need 1 state variable because 1 flip-flop can hold 1 state variable. And so going back, if you guys recall, 1 state variable has 2 states in it. So we have state A and state B. And so that's why here for my present state, I can just write Y. And then my next state, W0, W is 1. And then we'll have our outputs when for these. And for next states, let me just capital Y. And then for outputs, it's going to have W0 and W1. Probably look better if I flip these. So let me just do capital Y here, and capital Y is our next state, and then have W0 and W1 down here. And then our output is going to be when W0 or W1 because it's dependent on that current time compared to the more type, which it's the state after. And so it's dependent on the state right then. Okay, so our present states, we're going to have A and B. We only have two states, so that's why we have one state variable. And so for this, our two states, A and B here, one state variable is our Y. When W is 0, we stay in state A. And then when W is 0 for B, we go back to state A. When W is 1, we go state B. When W is 1, we stay in state B. Here for output, output here is going to be 0 when we're in state A. It's going to be 0 here still. The only time it's 1 is when we have been here and we stay in state B. That means when we remain in state B, it's this one right here, so Z is 1. Okay, now that we did the state table, we need to do the state assign table. In the state assign table, remember how I told you guys we only have one state variable, therefore we only have 0 and 1 for state variable. 0 is going to be, I'm just going to make that state A, then we're going to have 1 as state B. And so when we do our state assign table, what that's going to look like is, drop out for you guys, 1, 2, 3. Going to have our present state here. And then we're going to have our Y. And then we're going to have our next state. And then I'll just do the W0 just to save space. W1 here, it's fine. And then we're going to have our output Z, which would be W0 and W1. Okay, now that we talked about that, we're going to fill in this table just with those values we got here. So for 0 for A, 1 for B, 0, 0, 1, 1, and then here stays the same, 0, 0, 0. Okay, we got our state assigned table created. Now after state assigned table, we need to make equations in order to form the circuit. And so to make our equations, what we're going to do is I will make the K map for each one. And so for big Y is dependent upon W and Y, lowercase y. And so when I make my table over here, let me draw it out. And then we're going to have one for Z as well. And Z is dependent upon the present state and also the value of W here. So we're going to have those as well. So what we're going to have is our big Y on the first one we'll do, and then we'll just do so big Y here, and then we have our Z down here. Okay, remember that's because our big Y is dependent on the present state as well as the present input, where Z is dependent on our present state as well in the present input. And so what we're going to do here is we'll make our table because remember for the mealy types, when I did this Z, remember how it connected back from the first combinational block? That's why it's dependent on the present inputs as well. So here we're going to have our present state. I'll just do Y here, and then I'll have my W here. And then here's going to be my lowercase y as well, and my W here. When you see the circuit, you'll understand why Z and Y are dependent on both. And so I'm going to have my 0, 1, 0, 1, 0, 1, 0, 1. Okay, for 0, 0 here, what I'm going to get right now for Y and lowercase y. So when I have 0, 0 going here, 0, 0, that produced 0. When I had 0, 1, that produced 1. When I had 1, 0, that produced 0, and then I had 1 down here. And then for my W, for my Z, I had it go 0, 0, so that's 0 here and right over here. When I had 0, 1, I had 0, and I had 1 0, 0, 1 1. I had 1. Okay, now let's circle these. Here I can group these two together. Here I can just group this one. This big Y is going to be equal to, and then let's look, that'd be just W. This Z is going to be equal to, and it's going to be Y and W, lowercase. Okay, we got those equations made. We can now make our circuits. So let's go to our circuit building. And so for our circuit, remember we had two combination blocks and one for the flip-flops. And so combinational block 1 here, flip-flops in here, combinational block 2. What we're going to have, remember we have an input W. We're going to have an output Z for finite state machines. We're going to have one state here, so capital Y, and then our present state is going to be lowercase y. And then let's draw it out. And so we know what's going to happen is we're going to have our input coming in. Remember, it's a mealy type, so this is going to be connected to the output as well. And then we're going to have our, let's look at our equations, y equal to w, match it up here, y equal to w. And then this big Y is going to be the input for this D flip-flop over here. So we're going to have our D flip-flop. And the output Q is going to equal Y. Because our next state is going to have our present state now. And then our clock here, we're definitely going to have a clock coming in. So that'll probably be somewhere down here. And then remember, you have a reset for these D flip-flops. So that'd be our reset. Y is our reset. When it is 0, it's going to cause this to be 0 or output, and that will go to state A because that's what we want, 0. Remember, we signed up to state A, so when we have a 0 input for reset, that causes the output to become 0, and that's what we have for state A. So reset works correctly. And now we're going to look at our equations here. So Z equals W and Y. And so we have our W coming in here. We need our Y. So we're going to have these two. So it looks like an AND gate, and them together. Got the S or Z. Okay, hopefully that makes sense. That is your circuit diagram here. One thing I missed though, remember in the beginning how, oh, let me see. No, we're good. Because usually, remember how I usually drew it over here? We didn't have anything connected for a Y equation here, so we're good. Okay, that's our simplified blocks here. So that's how you would make a mealy type. And now that we made the mealy type, there's a state minimization using the partition method. I'm just going to say for that method, what you do is for the initial partition, you do all states in one block, and then you partition states that have different outputs in different blocks, and then you see what the 0 successors are. If they're in the same block, then you're good. Then you check the 1 successors. If they're in the same block, you're good. And then it may, if they're both in the same block, then they may be equivalent, and you check the next block in that partition, do the same thing. If they're not equivalent, then you have to break that block apart, and then you just go for all the partitioning method. At the end of the partition method, you can say that those specific states are equivalent, and then in the truth table, you can cross them out, the repetition ones, and replace where it mentioned the states you crossed out with that one state. So it's a simplification. Okay, let's go to the homework problems because he'll probably question you guys on those the most. So let me clear this real quick and then just show you how we're supposed to do those, because that's the important part behind this. Okay, so let me pull up my actual 301. Let's go to the Dropbox. Okay, so for homework 4, I believe that was the start. And then we'll look at So for homework number 4, the problem said a sequential circuit has two inputs W1 and W2 and an output Z. Its function is to compare the input sequence on the two inputs. W1 equals W2 during any 4 consecutive clock cycles, the circuit produces Z equals 1. Otherwise, Z equals 0. And so I looked here at the outputs and how I was like, okay, is this more or milli type? And so I was looking here and I was like, okay, when W1 equals W2 during 4 consecutive, I'm like, not equal, they're equal here. So I was like, oh shoot, they're equal here. And it happened in the same clock cycle right here. So I was like, milli type. If it happened at the next clock cycle, it'd be more type. And so that's how I determined it right there. And that's how I knew. So what I did here is when I listed it out, I assumed the starting state after reset would be state A, and the transition between the states occurs at the active clock edge. And for my algorithm, I had my states, so I was trying to think of them. So in state A, if W1's not equal to W2, remain in state A, and Z equals 0. So the number of states, how I knew is I was like, okay, well, if they're correct, then go to the next state. They're correct again, so that's twice. Correct a third time, correct a fourth time, then Z should be 1. And so that's how I knew I needed 4 states here, because I just saw I did the correct scenario. If they're equal 4 times in a row, then Z is 1. If they're not, Z is 0 for all the rest of these opportunities you can see here. Okay, so I put my algorithm together, and then I drew my state diagram here. So I'll do the correct scenario. So it goes here if they're equal, goes here if they're equal as well, goes here if they're equal as well, and then finally goes, if they're equal, it stays in D, and then Z would remain 1. However, if they're not equal, they all revert to state A if they're ever not equal to each other. That's when you go state A. And so when you hit reset, you also go to state A. So that's a big parts of my diagram here. And then I made my state table here from, so if they weren't equal, I set it equal to A. If they were equal, I did the next state like it should be. And my output was only 1 when it was correct 4 times in a row. Because for that to happen, this one had to go through B, C, D, and then remain in D. That means it's 1. It has occurred 4 times, that W1 is equal to W2. Okay, so we have 4 states. One flip-flop has 1 state variable. It can realize 2 states. However, we have 4, so we need 2 state variables, so we'll have 2 flip-flops. And for present state variables, it's the lowercase y2, y1. For the next state, it's the capital Y1, Y2. And so we're going to have 0, 0 state A. So therefore, when you reset on your flip-flops, the output's going to be 0 for Q. So it's going to start at state A. Then B, C, and D were the rest of the states here. We had no unused states, so that was nice. State assigned table. Here for my state assigned table, I had my present state for the A, B, C, and D. And then this was A, go back to A if they're ever not equal. And then here, go to B, go to C, go to D, and remain in D if they're equal 4 times in a row. And then for my output here, if they weren't equal, of course, it's always going to be 0. If they were equal, the first 3 times it was 0, but the last time it was 1. For this, what I had to do is because this was, okay, I'm going to try to explain this really well. It's an exclusive NOR gate. And the reason I put this here is because I couldn't write, when I had to write the equations in terms of, I couldn't write W1 not equal to W2 or W1 is equal to W2. So I had to substitute this expression up here with a variable here. So what I did is I created an exclusive NOR gate. And for my exclusive NOR gate, what happened in here is it would return 1 if the 2 were equal to each other. So they're both 1s or they're both 0s, it returns 1. But if they weren't, it would return 0. So they weren't matching. And so that's what I put here. So I put my output is going to be 0 if they're not matching. So right here, if they're not matching, it's 0. It's 1 if they are matching. And so my output Z, it would be 0 if they aren't matching, 1 if they are matching. And so then I find my equation. Shall I clear all this? If I find my y2 and y1 equation in terms of y and x, and so find the equation in terms of y and x. And so here I create my state, my k-maps, find the equations for them. Once I find my equations, I created my combinational blocks here, my left and my right ones. You can see what I did in here is from my equations, I legit wrote everything for the capital Y1 and then capital Y2 that all occurred in here. And for my Z, what it needed as well in the right combinational block here, I had my 2 flip-flops since I had 2 state variables because we had 4 states. And then when it was 0, 0, it would go to state A. So the reset was correct. I had the clock input to both. And that's how I did this homework. So now for homework 5, going back to what he wants. Homework number 5, write VHDL code for the finite state machine shown in this figure. And so what we had to do for the finite state machine is remember how I said, first you have to handle the state transitions, and then second, you have to do the outputs. And so here, I started with my library. I could include the arithmetic and unsigned. I should have done that just in case, but I wasn't doing any adding, subtracting, division. That's why I didn't include it. And so entity simple is my ports here. I have a clock going to the flip-flop. I have a reset going to flip-flop. I have a D coming in as an input here. I have an N as well. And then my output is going to be Z. And so that's what I have here is my inputs and my output. Then I end the entity, and then I do the behavior. The behavior of this entity, I have the type, the state type is, and so I have my S1, S2, S3, S4, S5. Because here we had 1, 2, 3, 4, 5 states. And then signal Y is going to be a state type because Y is what we assign the states to. So we're going to have a process. It's going to have our clock because it only happens on the clock active trigger edge because we have flip-flops here. That's going to affect the output, and the reset asynchronous signal. If reset is equal to 0, asynchronous gets priority, so that's why it's first. Then Y is going to go to state 1 here. That's where reset goes to. State 1 here. And then if not, then if it's an active clock, then it's going to run through all the states. So when S1 here, let me see, going here, S1, it's going to be when D and N are both 0. So in S1, if N is equal to 1, you're going to go to state 3 here, because look at this diagram. If N is equal to 1, you go to state 3. If N is equal to 1 again, you go to state 2. If N is equal to 1, you go to state 4. However, if in state 2, it's D is equal to 1, then you go to state 5. And then here in state 2, if D and N are both 0, you go, you stay in it. And then that's what happens here too. If they're both 0, you go up here, and then and then in state 4, if they're both 0, sorry, you go here to state 1. And then this from state 3, you go to state 4 if D is equal to 1, state 5 to state 3 if they're both equal to 0. So literally what I did with all these case statements down here is I just ran for all the possibilities and just assigned them. And so I was like, okay, if D is equal to 1, then go to this state. If N is equal to 1, go to this state. And so that's what I did here. And then I ended all of it. I ended the if statement, I ended the case, then ended the if, then end the process. Then I assigned the outputs here. So I did the state transitions all up there. Here's where the output is. So Z was 1 when the output Y was in state 4 or in state 5. You saw here in state 4, in here in state 5, Y put Z is equal to 1 there, else it was equal to 0. That was because if D and N were both 1 here, D and N were 1, it would not escape. It would only escape these states if it was 0. It would go back to the beginning. And so that's why they were either stuck in here unless the input was 0, which was the reset, and you start back at state A. Okay, Now he had 3 extra problems, which he assigned, which we'll do, and then that will conclude tonight, and you guys will be free to go. So let's do these problems. So 8.3 from the textbook. So let me pull that up. And 301. Okay. And problems 8.3. So 8.3 said derive the state diagram for a finite state machine that has input W and output C. The machine has to generate Z equals 1, and the previous 4 values of W were 1001 or 1111. Otherwise, Z is equal to 0. Overlapping input patterns are allowed. An example desired pattern is here. So when I see this, I just know Z is 1 when these 4 occur or when these 4 occur. Let's look down at this example here and see if it's a mealy or more type. 1001, I see that here. Looks like it went 1, so that looks like a mealy type. Let me see again. Here we got 1001 and it occurred on the same one. So that's a mealy type for sure. And we had our 111 here that occurred right here. And we had another 111 here, which occurred right here. And so it's for sure a mealy type. So that's what we know. So we know mealy. That's what we need to create it as. And so let's draw out, let's think of, so let me pull this up here. So let me, okay, so our algorithm in state A, if W is equal to 0, then we're going to, let's think about this. If W is equal to 0, then remain in state A, because that's neither one of the patterns. If W is equal to 1, then go to state B. Okay, I'm first just going to work on this one. So you guys know I'm just going to do the 111 case. So let's just do that one for now, and then we'll go to the other case. So in state A, if W is equal to 0, then go to state, oh shoot, because that's gonna, sorry, that's gonna be this case. I'm not gonna fill that one out. I'm just gonna fill out the correct one right now. If W is equal to 1, so we had a first one, then we had a second one, so going off this one, then go to state C. In state C, if W is equal to 0, then go to state, not going to fill that out right now, but W is equal to 1. That's the third one in a row. Then go to state D, and then in state D, if W is equal to 0, then go to state, not going to fill that out right now, but if W equals 1, that's the 4th time in a row, then remain in state D, and Z is equal to 1. Okay, so here we go. We got all that algorithm created for the correct one of 1111. Now we're gonna have to create the algorithm for 1001 as well. So let me just go back up here and put in 0 for all these ones before. Okay, so for 1001, that would occur right here. So if W is equal to 0, then go to state, I'm going to create a new one here just because it's a different pattern. So go to state E, C is equal to 0. And so that's 1, 0, and then the next 0. So in state E, if W is equal to 0, then go to state F, and that would be Z is still equal to 0. You need one more 1, right? Let me see, because we had 1, 0, then we went to state E, 0, and then this would be the other state is equal to 1. I'm going to leave that blank right now and go to, don't know yet. If state F, if W is equal to 1, that'd be 1, 0, 0, 1. Then it's 1, 0, 0, 1. Okay, let me see on that. Equal to 0. That pattern would be broken. So, so I know this would be correct. The pattern Z is 1. Okay, so what we determined here is we had a 1, and then we had the 1, and then we had the 1 and 1, and then that made Z is 1. Then we have the 1, 0, 0, and then, oh wait, sorry, the 1, the 0, and then down here, 0, and then finally that's the last 1, and that sets the output equal to 1. Okay, now we have to find out all those cases when it's not. So let's go through each and see. Looks like we stopped here. So if W is 1, so we start out 1, and then it's 1 again, and then we get a 0. So that means we could still follow the pattern of 1, 0. And so that would mean, so 1, 0, that would be the same as going here, 1, 0. So I'd say go to state E, which would be 0 as equals 0. So then that'd be 1, 0, because it would hit here and be 1, 1, 1, and then let's say it hits 0, then it would go to state E, and then in state E, it would check if it's 0 and then 1. So that could be the 1, 0, 0, 1. Say in the beginning it was 1, 1, 0, 0, 1. We would check the 1 right there. So that'd check our 1, 0, 0, 1. Okay, let's try our next one. So we have 3 1s, and then we're going to go to, then there's a 0 that pops up that looks like, so we have 1, 1, 1, then we have 0. So then that could possibly start this one. So then go to state E, because 1, 0, then if the next one is 0, and then here, that'd be, so if we had 1, 1, 1, and then we get a 0 all of a sudden, that still has the pattern of 1, 0. And so then it would check the next 0 here. And then in state F, it would check if it's 1. And then that could complete this pattern here. So go to state F, but if W is equal to 1 here, so we would have 1, 0, and then here it would be 1. So that would start back at the beginning where we would have 1 here. So go to state B. Z is equal to 0, because that would be 1, 0, 0, and then you would get here, and then no, it'd be 1, 0, 1, and then you're like, oh shoot, then you get a 1. Well, that can start either pattern. So because it can start either pattern with the 1, that has to go to B because you only have 1 in the beginning. Okay, and then here in state F, if we get the 1, 0, 0, 0, then we're like, oh shoot, if we have 1, 0, 0, 0, that's no pattern at all. And so then that would then go to state A. That'd be Z, 0. And then if we have 1, 0, 0, 1, okay, if it's 1, 0, 0, 1, it's going to have to go back to the beginning. So then go to state B, because that's where the first one would occur, because it can't do any pattern after. Okay, so we got those all. Okay, I'm going to draw the diagram because that's super confusing, and it took me a while to understand that when I did it before for practice. So let me draw the diagram and see if that helps you guys. It's a really weird problem. I don't think you would throw this on the exam, but it's good practice. Okay, so state diagram. We have 1, 2, 3, 4, 5, 6. So I'm going to have 1, 2, 3, 4, 5, 6. Okay, we have 6 of those, and we're going to have state A, state B, C, D, E, F. What I suggest is on the exam, you don't understand it, do the one you know. You know the 1, 1, 1, 1, and how that will create Z as 1. So let's do that first. So if W is equal to 1, it's going to go to state B. So say W is equal to 1. And then if W is equal to 1 again, it's going to go to state C. And then if W is equal to 1 again, it's going to go to state D. Got 3. And then finally, if W is equal to 1 again, then, oh wait, we're going to remain in state D here. I forgot the Z's. I know, John, you're probably going to tell me. So here Z is equal to 0. C is equal to 0 here. C is equal to 0. And then down here, W equal to 1. That means Z is going to be equal to 0 down here. Okay. Sorry, 1. Let me erase that. W is equal to. Okay. So we got A, B, C, D correct. And so that's if we have the 1, 1, 1, 1. Now we're going to go to the 1, 0, 0, 1. So I'm just going to show you guys how I was thinking of it. So we have the 1 here, then we get a 0. So if we get a 0, then we're going to go to state E here. So this would be the 1, 0. Z is equal to 0. Z is equal to. So 1, 0, and then 0 again. Let's go to W is equal to 0. So Z is going to be equal to 0. And then, so 1, 0, 0. And then we have 1 at the end. And so that would mean here, then if we have 1, it's going to be W is equal to 1. And then Z would be equal to 1. But since that, let's say F, it's going to go to, sorry, not there. Let me erase that real quick. It's going to go here because that could start possibly a new pattern of the 1, 1, 1. If we have finally the W equal to 1, C. Okay, so we got the 1, 0, 0, 1 pattern established. Now we did the 1, 1, 1, 1 as well. So these are the ones we did. We did this one here, this one here, this one here, this one here. And then we did the 1, 0, 0. Oh, wait, sorry. 0 in state 0. And then 1. Okay, now we need to do the other ones that are missing. So in we have our reset N here. And then if it's equal to 0, then you stay in A. So W is equal to 0. Then Z is going to be equal to 0. Got that top one done here. And then next one was in state C. If it's equal to 0, then you're going to go to state D. So then our next one is in state D here. W equals 0, go to state D. And then our next one was in state E, if W is equal to 1, then go to state B. Oops. So W is equal to 1, then you go to state B. Okay, I'm sorry, W is equal to 0. Then you go to state, oh, yeah, that's correct. Okay, we did that one. And then our final one here is in F. W is equal to 0, then go to state A. So here, W equal to 0, go to state A. So W equal to 0, and Z is equal to 0. Okay, so what we have here hopefully this sort of made sense. You probably won't understand it the first time, it's a little weird. So you had the 1, 1, 1, 1, and that produced the 1. So that was the correct sequence. Remember, other sequence was 1, 0, 0, 1, and 1. And then that produced the Z as 1. The other instances were when the pattern was not correct, but it could possibly start a new pattern. And so if you ended on a 1, that should start in here because that could possibly start the 1, 1, 1 pattern. And then those were the other ones. So that problem was a little strange for sure, but we'll go to the next one. The next two aren't bad at all. That one was just weird. Okay, so he assigned for the next one, 8.4. 8.4. Write VHDL code for the finite state machine in problem 8.3. Oh, okay. So right here is all my algorithm. So let me open up a new one here. And what we're going to do is I'm going to start it out so you guys know how to code. This library IEEE use IEEE.standard logic dot, or sorry, 1164.all. Use IEEE.standard logic arithmetic dot all. Use IEEE.standard logic and then unsigned. You don't need these because they're not the last two because they're not using addition, subtraction, division, multiplication, but I just like it so I don't forget. And then entity, and this is Mealy, I'll call it, is, and then remember you have a port, you're gonna have your clear, you're also gonna have your reset N, you're gonna have, because those go into the flip-flops, oh sorry, the clock, reset N, and then for a Mealy type, you're gonna have input W, and it can either be 0 or 1, so it's standard logic. You're gonna have output Z. Oh wait, sorry, that'd be the other one. If these were input standard logic, and then you're gonna have output Z, which is standard logic. And you're gonna end Mealy. And then you're gonna have architecture, behavioral of Mealy is, and then you're going to have within your architecture behavior, remember I told you guys the most important 2 lines you write is the state type ones, because those are going to be what you'll see the most. And I'm already calling it, people are going to forget this, so you guys need to know it. Be up ahead. So type, state, type, and then how many states do we have here? 1, 2, 3, 4, 5, 6. Okay, so our state type is A, B, C, D, E, F. Okay. And state type, and then we're gonna have, oh sorry, signal Y, and Y is gonna be a state type. Okay, got our signal in here, we got our state types in here. Doing pretty good. And then we're gonna have to begin the architecture. And when we begin it, we're gonna have the process. And the process is gonna be based off the clock in reset N. Okay, and then begin process. Yes. Yeah, welcome, Brandon. Yeah, don't worry, I'll upload this for sure. We'll be done in about 10 minutes. So thanks for coming. Okay, so we're gonna begin the process. And within our process statement, we're going to have our if reset N here, because asynchronous has the greatest priority. Remember that. If reset N is equal to 0, active low, then, and we can use an if statement because it's inside a process, reset N is equal to 0, then y is going to be state A. Else, if clock event, we need an active clock edge to change it. If not, clock event and clock equals 1. Then what we're going to have is case of y. And so case of y, the cool part is when, in the when is A in that state. And then within the, so when it's A, then it's going to assign y is going to be, oh wait, I need an if statement in here. That won't work. So if w is equal to 0, then y is going to be equal to A. Else, if
I think you forgot is after case y.
is y, let me check. Yes, you're correct. Good job. Nice eye.
Okay.
Here, else if w is 1, then we're going to go to state B. Then, and if when b w is equal to 0, then y is going to be equal to e. And then else if w is equal to 1, then go to state C. And okay, got those in. Else if then, just remember those. Okay. And if statements, okay. Then after we did that, now we're gonna go state case C. Let's start copying some of these. Okay, in C, if it's 0, then go to state E. If it's 1, go to state D. And then do next one. When it's D, if it's 0, then go to E. If it's 1, go to D. And that's the exact same. And then in state E, W is equal to 0, then go to state F. If W is equal to 1, go to state B. Then our last one, when F, if it's 0, go to state A. If not, go to B. And then we're going to end this case. We're going to end the if. We're going to end the process. And thank you. And then we're going to have our next one, which is we need to assign the output. And remember in the Mealy type, the output, it's going to be a little, it's not based on the state, it's based off the value of W then. And so when we're in that, let me check real quick. I want to make sure I do this correctly for both. Okay, so what we're going to have here is we're going to have another process statement checking the value of W and the case. So in here, we're going to have a process. So it checks the case it's in and it checks the value of W. Okay, it does not want to, okay, there we go. Begin. And so when we begin our process, we're gonna have case Y again is, remember the is this time, and we're gonna have when A, 1, 2. So when it's, sorry, the only one where it's gonna actually be 1, let's just look at the specific cases when we actually have Z is 1, that's gonna be in state D. So when D if W is equal to 1, then Z is going to be equal to 1. And then if, and then the other time when it was when in state F, if W is equal to, and then here we're going to have 0, 1. Then we're going to say, then Z is going to be equal to 1. And case, oh, sorry, then end process. Okay, and then end behavioral. Okay, so there we have when we sign it, but the other thing is if it's not here, so this would be for this case, and then I need to put in Z is going to be 0 otherwise. Here it would assign 1 when it goes in those cases, so it would not change it. So when others, and Z is going to be equal to 0. Okay, and then that ends everything here. So in this process statement here, this is where we assign the output. This one here is where we do all of the state transitions. And so that should be the code for this one. So if we match it up against theirs, we notice they have the clock, they have the reset N, they have the W, they have the Z. They the state type is A, B, C, D, E, F. They did the signal Y state type. They began the process clock reset N. They began the process. Then they oh, sorry, I don't need this begin right here. I mean the process there. If reset N is equal to 0, then Y is equal to A. If it's clock event, clock is 1, then case Y is it's going to be A. When if 0, then it's going to be A. If 1, then it's going to be then it assigned it B. It just did else. I just did else if. You could do just else here. 0, it's going to be E, 1, C, and then here, yeah, that's all correct. And then for their statement here, they did the parallel process of Y and W. And then they said if, oh, okay, they did a different way where I did the case Y when D, and then I did if. And so I did it just a different way. Their way is correct as well. Either one will work, and that should be good. And then the last one of the night. The only one here is John. And so let's do the partition method. And so problem 8.18. Figure 8.59, assume that the unspecified outputs in state B and C are 1 and 0 respectively. Derive the minimized state table for this finite state machine. Okay. So let's go to 8.59. Here it is. Okay. So here is our state output table. And with partitioning, Dr. Koo had a specific method that he wants to make sure we follow. Okay. What he talks about is when we have these unknown values in here, the don't cares for the states, the next state, leave as is. However, the don't cares on this output one, you're either going to make them all 1 or all 0. For this example, let's make the don't cares just 1 to make it easy. Let's make this one 1 to just make it easy. Okay. Well, we know from here, we have one input W. We have one output Z. And then we also have 7 states, A through G. We know the output here, big thing, if your output has W0, W1, that means mealy type. So we know this is a nullity. Okay, output depends on the state and the input. And so let's make a partition in the beginning. So our partition to start out here. Let me go over here. So P of 1, so let me make this a little larger. P of 1 is going to equal, and our P of 1 is going to be all the states together in one. A, B, C, D, E, F, G. And what we do is all states in one block. You're going to group them based on their output. So here we see that all the states are 0, 1, except these two here. A is 0, 0, and C is 0. Oh, sorry. D is 0, 0 as well. And so those are different. So we're going to group them differently. So for P2, it's going to equal A and D are grouped differently due to their outputs than B, C, E, F, G. Okay, now that we group the states based off output, group based on output. Now for the AD block, the 0 successors are, look at AD here, A, 0, B. D is B. That's in the same block. Yay. Okay, for the B, C, E, F, G block. Oh, sorry, I forgot to check the 1 successors. The 1 successors are for A, it's C, and for D, it is G. And so what we have here, C and G, they're in the same block, we're good. Okay, for the BC, E, F, G block, the 0 successors, I'm going to abbreviate it, are, and then B, it's going to be D, for C, F, for E, F, for F, E, for G, F. And then 1 successors are, and then the 1 successors are, here we have the don't care. For the C, it's going to be E. For the E, it's going to be C. For the F, it's going to be D. And for the G, it's going to be don't care. ECD, D is in a different one, not in the same block. Look, the D is in this block where the EC are in this block here. And so not in same block, sad face, because I have to retype this. Not in the same block. And so now what we're going to do is we're going to have to split it up. So P3 is going to equal, so since they're not in the same block, we take it back. So E was in this block, C was in this block, D was not in that block. D was the 4th one over, so that's F. So we're going to partition it, and F's going to be in its own now. So we're going to have our A of D, we're going to have our F, and then we're going to have the B, C, E, G. 0 successors are, and then the 0 successors in this block, we know for the AD1, oh, sorry, I need to do it for the AD block. For the AD, oh, I'll just copy it here because honestly it's the exact same. That's the same. For F, we don't care what the 0 successor are because it's literally going to be in the same one because it's only 1. 0 successor for F is in E, 1 successor is in D. Of course, those are going to be the same because it's only 1. Now we're going to do the next block. Let me go up. And then for the B, C, E, G block, the 0 successors are D, it's going to be D, C, F, E, F, G, F. So D, F, F, F. Okay, 1 successors are for B, it's going to be don't care. C, it's going to be E. For E, it's going to be C. And for G, it's going to be don't care. Okay, we got these two created. And so P4 is equal to, okay, we got the AD, we got the F, we got the BCEG. And oh wait, sorry, did I check if these are in the same? Yeah, EC are in the same block. DFF, no, these are not in the same block. Sad face again, because D is in this block, F is in this block, and so when we look at this, I'm just gonna call D out because that's the only one not in that block. So separate B from this. So because that was in its own block, D and F, all the others were in the same one. So let's take F out. So for P4, it's gonna be equal to AD, and then we're gonna have our F, and then we're gonna have our B, separate, partition that one, and we're gonna have CEG. Okay. For the AD block, exact same thing, we're good. And then for the next ones here, let me erase this. Okay. For the one down here, for the F and for the B, we don't care, it's only one state. Of course, it's gonna be the same. For the CEG block, what we're going to have here is it's going to be FFF, and it's going to be EC, checking here, FFF, same block, EC in the same block. So we're good there, and then we should be fine. So AD, it's BB in the same one, CG in the same one, FFF in the same one, and EC in the same one. So that means right here, we are good. So P5 is going to equal the exact same thing. We did not have to break it up any further. And so then P4 is equal to P5. And so then our conclusion is that A and D are equivalent. Use A to represent. And then C, E, G are equivalent. Use C to represent. Okay, now in our state diagram, what that means is here, let me clear this real quick. That's a little confusing. Okay, what we did again, we just put in one for this, and one for this for don't care. Okay, so since A and D are equivalent, we're only going to use A to represent. So we're going to take out D here in this column. Then anywhere we see a D, we're going to replace with an A here. So let me put in A. Okay, and then for CEG, we're going to take out E and G. So let me take out E and G here. And then our where we see E and G, we're going to replace that with and a C. C here and C here. Okay, and then that should complete our state diagram. I mean, our state assignment table. And so going back here, let's check our answer for the minimize. Oh shoot, what did we do wrong? Let me check real quick. A, B, C, D, E, F, G, A, D, we split up. They split up. Oh wait, they grouped it. Oh shoot, they grouped it differently than me. Do you remember, John? Oh, it says if we assign different values to the output don't cares, we'll get a different result. And so here we got a different result since I assigned ones where they assigned zeros to those don't care. So,
That answer key looks to be different from the one. Oh, wait, actually.
but instead, what they did differently, see how here I put ones, they put zeros for those. So they grouped it based differently on their output. And I wrote down a note from Dr. Q. It says, if you assign different values to the output, don't cares, you will get a different result. So that's probably why we got a different result for our output. So we did it another way. but that should be it. So that is all, and I'm going to stop the recording.